Hello there, and welcome to the Sleepy Science Channel. Maybe you've had a long day, or maybe you just like falling asleep while thinking about stars and galaxies, rather than counting sheep. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your thoughts slow down. Allow your breathing to soften, and notice your body feeling lighter, as if gravity itself has eased its grip. Tonight, we drift into the quiet wonder of the Milky Way galaxy, the vast river of starlight we call home. A place shaped by distant suns, unseen forces, and structures so immense they unfold far beyond imagination. It turns slowly in the dark, carrying ancient worlds, clouds of energy, and cosmic wonders hidden in the darkness. The Milky Way holds countless mysteries, each one stranger than the next. If you enjoy these gentle journeys, consider liking, subscribing, or sharing a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, if you're ready, let's begin. The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. Even now, it continues to gather material, gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that feed its halo. It grows not like a living thing, but like a gravitational structure deepening over time. Some of this growth happens quietly, through drifting clouds of cosmic dust. Other times, it comes with disruption, as satellite galaxies are torn apart and their stars scattered across the sky. The galaxy you live in today is not the same one the dinosaurs saw, and the one your distant descendants may know could be larger still, stitched from the ruins of 1,000 smaller worlds. We still don't know how many arms the Milky Way has. It seems like something we should know. How many arms spiral from the center of our own galaxy? But from our position deep inside the disk, it's hard to see the whole structure. Dust clouds obscure distant regions, and stars blur into one another. For decades, astronomers believed there were 4 major spiral arms. More recent observations suggest it may be fewer, or that the arms twist and split in ways more complex than expected. Some fade into fragments, others wrap around unexpectedly. The Milky Way may not be a neat pinwheel at all, but a living, layered swirl of stars shaped by forces we still don't fully understand. Some stars in the Milky Way are older than the Milky Way itself. Not every star in the Milky Way was born here. Some ancient stars, wandering in long, tilted orbits, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars may have originated in smaller, primordial galaxies that merged with our own billions of years ago. Their chemical fingerprints show almost no heavy elements, suggesting they were born shortly after the Big Bang. They move slowly and high above the galactic plane, remnants from a time long gone. In their light, we glimpse a universe that was younger, wilder, and still learning to become what it is. Our solar system orbits the center of the Milky Way at over 828,000 kilometers per hour. That's more than 230 kilometers every second. And still, it takes about 225 million years to complete just one loop around the galaxy. This orbital path is what we call a galactic year. In Earth time, we've only gone around the Milky Way about 20 times since the solar system formed. When the first dinosaurs appeared, we were in a different part of the galaxy entirely. The stars we see today weren't always nearby, and won't always remain. Everything is in motion, quietly, slowly, endlessly. Even as we sleep, the Earth turns, the Moon circles, and the entire solar system sweeps forward through a galaxy in motion. The Milky Way holds worlds larger than Jupiter, but float alone. Scattered throughout the galaxy are enormous planets that drift freely without orbiting any star. These rogue giants can be larger than Jupiter and wander through space in cold silence. They likely formed in young planetary systems, but were later flung out by gravitational interactions with other large bodies. Once ejected, they continue on solitary paths, illuminated only by the faint glow of their internal heat. Some of these planets may still retain thick atmospheres that trap warmth. Others may harbor swirling storms that churn slowly in the deep dark. Detecting these worlds is challenging because they do not reflect starlight. Instead, astronomers search for the faint infrared radiation they emit, or watch for subtle gravitational effects when they pass in front of distant stars. These lonely giants reveal how dynamic and chaotic planetary systems can be. Their existence suggests that planets are not always bound to the stars that formed them. Instead, they may roam indefinitely through the galaxy, traveling far from any warmth or light. These wandering worlds add a quiet and mysterious dimension to the Milky Way's population of planets. There are stars that feed on their companions. In some binary systems, one star grows dense enough to draw material from its partner. This process can occur when a star becomes a white dwarf, neutron star, or black hole. The stronger gravitational pull of the compact object strips gas from the companion's outer layers. This material forms a swirling disk around the feeding star, heating up as it spirals inward. The interaction can produce bursts of radiation that appear as bright flares in the sky. Over long periods, the feeding star may gain significant mass, altering its behavior and sometimes setting the stage for future explosive events. The star being consumed may lose much of its outer envelope, changing its structure and evolution. These dramatic relationships reveal how closely paired stars can influence one another. They show that stellar life cycles are not always solitary. Instead, some stars grow by taking material from their neighbors, creating systems shaped by both cooperation and conflict. These feeding stars remind us that even distant suns can experience intense and transformative interactions. The Sun has completed fewer than 25 galactic orbits. In all of its 4.6 billion years of existence, the Sun has only circled the Milky Way around 20 times. That's fewer than you might expect, considering its incredible speed, nearly 830,000 kilometers per hour. But the galaxy is so vast and the Sun's path so long that each orbit takes hundreds of millions of years. We often think of the stars as ancient and unmoving, but our solar system is still young on a galactic scale, a newcomer in a city of older, more traveled suns. We are part of the galaxy's motion, but still early in its long, winding story. The Milky Way's rotation defies Newton's predictions. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as outer planets move more leisurely around the Sun. But in the Milky Way, stars in the outer regions orbit almost as quickly as those near the center. This defies classical expectations. The reason, astronomers believe, is dark matter, an invisible, unknown form of mass that surrounds the galaxy in a vast halo. Without dark matter, the galaxy would not hold together. With it, the math works. The Milky Way turns like a solid wheel, not because we understand it fully, but because something unseen is holding it in place. The Milky Way hums with cosmic radiation. Beyond visible light, the galaxy glows with more mysterious forms of energy. Cosmic rays, high-energy particles born in supernova and distant galaxies, stream through space and pass through your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds, pulsars, and the cold breath of hydrogen. These invisible hums reveal what light cannot: the violence, magnetism, and ancient fires still flickering within the galaxy's bones. When you look into the night sky, you're only seeing a narrow band of the Milky Way's true spectrum. Beneath the stars, the galaxy hums softly in many colors, many frequencies, a hidden symphony in the dark. There are double planet systems that orbit each other like dance partners. Not all planets revolve around stars alone. In rare cases, two planets of similar mass form close enough to one another that they share a mutual orbit. Instead of one dominating the other, the pair circles a common center of gravity located between them. These double planet systems move through space like partners performing a slow and graceful dance. Their shared motion affects their rotation, their tides, and their long-term stability. Finding such systems is challenging because they often resemble single planets when viewed from afar. However, detailed observations can reveal small variations in their orbits that hint at their dual nature. These systems provide insight into how planets form and interact. They show that worlds can develop in cooperative pairs rather than solitary paths. The existence of such arrangements highlights the diversity of planetary configurations possible in the Milky Way. Imagining two planets bound together in a cosmic waltz adds a touch of elegance to the vast and varied structures scattered across the galaxy. Some stars are shaped into flattened spheres by extreme rotation. Certain stars rotate so quickly that they become noticeably flattened. Their equators bulge outward due to centrifugal force, while their poles remain more compact. This shape affects the distribution of temperature across the surface. The poles tend to be hotter and brighter because the material there is more compressed, while the equator can appear cooler. This phenomenon is known as gravity darkening. Rapidly rotating stars are often young and massive, still carrying the angular momentum of their formation. Their rotation also influences how they evolve. Fast-spinning stars can mix their internal layers more efficiently, changing the way they burn fuel. Observing these stars helps astronomers understand the complex interactions between rotation, structure, and energy output. Their distorted shapes challenge the simple idea of stars as perfect spheres. They reveal that even familiar-looking points of light can hide unusual physical behavior. These flattened stars add another level of diversity to the Milky Way, showing that rotation can sculpt a star into forms very different from the ones we see near home. The Milky Way has already collided with other galaxies, and it will again. Our galaxy may feel like a stable home, but it is built from the wreckage of others. Over billions of years, the Milky Way has absorbed smaller galaxies, drawing them in, unraveling them, and scattering their stars into tidal streams that wrap around the disk. One such galaxy, the Sagittarius dwarf, is being pulled apart right now. And far off in the night sky, Andromeda is drifting slowly closer. In about 4.5 billion years, the two great spirals will merge in a cosmic collision. Stars will almost never hit each other, but the galaxy's shapes will change forever, folding into a new form, vast and quiet. Even galaxies are not eternal. They evolve, collide, and begin again. The Milky Way holds regions filled with primordial hydrogen. Scattered throughout the galaxy are pockets of hydrogen that have remained largely unchanged since the earliest eras of the universe. These regions contain gas that existed before many generations of stars were born. While much of the hydrogen in the Milky Way has been processed through stars and enriched with heavier elements, these primordial areas preserve a simpler chemistry. Their presence helps astronomers trace the early history of the galaxy and understand how it grew from smaller structures. These clouds are cold, faint, and difficult to detect, yet they play a vital role by feeding material into star-forming regions. They also allow scientists to compare modern galactic environments with ancient ones. Primordial hydrogen stands as a quiet reminder of the universe's beginnings, still drifting through the arms and halo of the Milky Way. There are stars that collapse into dense remnants without exploding. Not every massive star ends its life in a bright supernova. Some collapse directly into dense remnants without producing an outward explosion. This quiet collapse occurs when the internal structure of the star fails rapidly, causing its core to form a black hole or neutron star with little visible disturbance. The outer layers may fall inward instead of being blasted into space. These silent endings are difficult to observe because they produce few obvious signals. Astronomers search for missing stars that fade without explanation, or look for subtle gravitational effects that indicate a compact remnant has formed. These quiet collapses help scientists understand the thresholds that separate explosive endings from silent ones. They reveal a more complex landscape of stellar death, where the final moments of a star's life depend on delicate balances of mass, rotation, and internal structure. Some worlds are born in chaotic multiple star systems. There are planetary systems in the Milky Way that form within groups of 3 or more stars. These environments are filled with shifting gravitational forces that influence the paths of growing planets. Dust and gas disks twist and wobble, shaping planets that must find stable orbits amid competing tugs. Some planets end up circling one star in the group. Others find orbits around pairs of stars. In rare cases, planets may orbit all the stars together in wide loops. The chaos of these systems creates a wide range of outcomes. Some planets are ejected and become rogues. Others survive in balanced orbits that remain stable for long periods. Studying these complex systems helps astronomers understand how planets form under extreme conditions. They show that planetary birth can occur even in environments filled with disorder and constant change. The galactic center contains whirling disks of hot dust. Near the Milky Way's core, swirling disks of dust encircle the central black hole. These disks glow brightly in infrared light because the dust grains absorb intense radiation and heat to high temperatures. The material moves in fast, spiraling paths shaped by gravity and magnetic fields. As the dust orbits, it interacts with surrounding gas, creating structures that shift over time. Observing these disks helps astronomers understand how material flows toward the black hole and how energy from the core affects the surrounding environment. These glowing spirals reveal the dynamic nature of the galactic center. They show that even dust behaves dramatically when placed in such powerful conditions, forming elegant structures that twist in the deep gravitational well. Some stars are kicked to extreme speeds when their companions explode. When a star in a binary system explodes as a supernova, the sudden release of energy can disrupt the delicate balance that holds the pair together. If the surviving star is flung outward at the right moment, it can be propelled to extraordinary speeds. These runaway stars move far faster than typical stars in the Milky Way. Their high velocities reveal the violent events that set them in motion. As they travel, they carry with them the chemical signatures of their original environments. Studying these stars helps astronomers understand the outcomes of stellar explosions and the dynamics of binary systems. Their rapid motion also provides clues about the gravitational landscape of the galaxy. These swift stars remind us that even the seemingly peaceful sky holds records of dramatic and energetic processes. The galaxy contains solar systems with planets that circle in wildly tilted orbits. Not all planetary orbits align with the equators of their stars. Some planets move on steeply tilted paths, circling their stars at sharp angles that differ greatly from the orbits of their siblings. These tilted orbits can arise from past interactions with other planets, passing stars, or the gravitational pull of a distant companion. The unusual angles affect the climate and long-term stability of the planets. Seasons can become extreme, and the length of daylight can vary dramatically. Observing these systems helps astronomers understand the chaotic processes that shape planetary architecture. The presence of tilted orbits shows that solar systems can evolve in surprising ways, creating arrangements far different from the orderly pattern seen in our own system. These worlds highlight the diversity of planetary motion in the Milky Way. Some worlds are covered in ice that never melts. In the far reaches of the galaxy, or in systems where stars emit only faint heat, some planets remain frozen from surface to core. Their icy crusts can extend for kilometers, sealing away oceans or rocky interiors beneath solid layers. These worlds may have atmospheres too thin to trap warmth, or may orbit stars so cool that temperatures never rise above freezing. Some exist as rogue planets drifting in total darkness, where internal heat gradually fades until the surface becomes completely frozen. Although these planets seem quiet, their interiors may still harbor activity if enough heat remains from their formation. Studying frozen worlds helps astronomers understand how planets lose heat and how different environments evolve. Their silent, unchanging surfaces contrast sharply with the dynamic weather and geology seen on warmer planets. These icy worlds show that the Milky Way contains environments where cold dominates completely. The Milky Way holds electric-charged nebulae that glow with ghostly light. Certain nebulae in the galaxy emit a faint, eerie glow created by charged particles moving through magnetic fields. These electric-charged regions occur when energetic radiation strips electrons from atoms, creating ionized gas. As electrons recombine with ions or move through magnetic structures, they emit soft, ghost-like light detectable in various wavelengths. These nebulae often form near hot stars or in regions shaped by past explosions. Their appearance reveals the presence of powerful forces acting on the gas. Observing them allows astronomers to trace magnetic fields that are otherwise invisible. The glow carries information about temperature, density, and the processes that energize the gas. These nebulae add a subtle, ethereal beauty to the Milky Way, showing that even faint light can tell rich stories about the energy flowing through space. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth. By studying these signatures, astronomers can trace a star's history. Some stars are rich in heavy elements like iron and calcium, suggesting they formed in dense metal-rich regions. Others are nearly pure hydrogen and helium, born when the universe was still young. These differences allow scientists to group stars into families, uncover ancient mergers, and reconstruct the hidden story of the Milky Way's formation. In this way, chemistry becomes a kind of time machine, letting us read a star's past like a line of ancient poetry written in light. The sky is full of stellar streams from shredded galaxies. Across the sky, thin ribbons of stars stretching arcs and curves, barely visible, but unmistakable when mapped with precision. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart. As they orbit, their stars are smeared across space by tidal forces, forming long, delicate trails that trace their former paths. Some wrap around the galaxy like ghostly halos. Others dive in toward the core. These streams are evidence of past collisions, quiet mergers that built the Milky Way over billions of years. The galaxy, like a tree, carries the rings of its past in every thread of light. The Milky Way is warped. Our galaxy doesn't lie flat like a perfect spiral. Its disk bends upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warp, was invisible to us until radio telescopes mapped the hydrogen gas that stretches far beyond the starlight. Astronomers believe the distortion may be caused by satellite galaxies tugging gently on the Milky Way's edges, or by clumps of dark matter bending the structure from below. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still. Over time, they bend, flex, and change form in response to invisible forces. From a distance, the Milky Way might look like it's dancing slowly through space. You can only see about 0.000003% of the Milky Way with the naked eye. Under a clear, dark sky, far from cities and streetlights, you might see a few thousand stars. To the human eye, that seems like an ocean of light, but it's barely a droplet. The Milky Way contains over 100 billion stars. Most are hidden from view. Some lie behind thick curtains of dust. Others are too faint or far away for our vision to reach. The pale streak of the Milky Way that crosses the sky on moonless nights is just the innermost whisper of the whole. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us, too vast to grasp from within. There are dense clusters where stars live only a light year apart. In certain regions of the Milky Way, stars form in such high numbers that they end up packed very closely together. In these dense clusters, the distance between neighboring stars can be as small as 1 light-year, far closer than the distance between the Sun and its nearest companion. The intense gravitational pull within these clusters influences the motion of each star. Their combined light creates brilliant scenes that would fill the sky for any planet orbiting within such a cluster. Over time, these groups gradually lose stars as gravitational interactions push some outward. However, the densest clusters remain tightly bound for long periods. Studying them provides insight into the earliest stages of stellar evolution and the environments in which many stars are born. These compact clusters show that the Milky Way contains regions of both solitude and incredible crowding. They offer a glimpse into the vibrant communities where stars begin their lives. The galactic center contains arcs of energized gas that twist like ribbons. Near the heart of the Milky Way, clouds of gas become energized by the intense radiation and magnetic fields surrounding the central black hole. These forces shape the gas into long, graceful arcs that twist and curve like ribbons in the dark. The structures glow in radio and infrared wavelengths, revealing their delicate outlines. Many of these arcs trace the paths of magnetic fields that thread through the region. Others form where energetic particles collide with gas, creating bright filaments. Observing these ribbon-like shapes helps astronomers map the complex interactions at the galaxy's center. They show how gas flows, how magnetic energy is distributed, and how past events have influenced the environment. Although these arcs may appear serene, they are shaped by powerful and dynamic forces. Their graceful forms add an unexpected beauty to one of the most extreme places in the Milky Way, where energy and gravity continually sculpt the surrounding space. Some worlds orbit stars that flare with intense radiation. Throughout the Milky Way, certain stars pulse with sudden bursts of radiation that surge outward like brief shocks of energy. These flares are caused by rapid changes in the star's magnetic field, releasing heat and light far stronger than the star's usual glow. When a planet orbits close to such a star, it experiences sharp waves of radiation that can heat its atmosphere, disrupt its chemistry, or gradually strip away its upper layers. Yet some planets endure these harsh conditions, developing atmospheres that adapt over time. Observing these systems helps astronomers understand how flares shape planetary environments and influence the potential for habitability. The intensity of the flares varies, with some stars erupting only occasionally, while others release bursts on a frequent schedule. These planets experience skies that can brighten suddenly, transforming their atmospheres with each flare. The idea that entire worlds orbit such volatile suns adds a dramatic sense of diversity to the galaxy. It shows that life and stability are shaped by forces far beyond simple sunlight, and that stars themselves can be restless, changing the conditions of any world that circles them. The Milky Way holds enigmatic gamma burst sources. Hidden throughout the galaxy are rare objects capable of releasing brief flashes of gamma radiation, the most energetic form of light. These bursts are sudden, short-lived, and incredibly powerful. Some occur when dense stellar remnants collide, while others may form through magnetically driven events in compact stars. Because gamma bursts happen quickly and fade rapidly, they are difficult to observe. Instruments must be watching at exactly the right moment to detect them. When these bursts are captured, they provide valuable insight into extreme physics. The energy released in a single burst can exceed the total output of many stars combined, yet the event may last only seconds. These powerful flashes illuminate the environments around their sources, revealing conditions that cannot be reproduced anywhere else. Studying them helps astronomers probe the nature of magnetic fields, gravity, and dense matter. Even though these bursts are rare, their presence shows that the Milky Way hosts events of astonishing intensity. They offer glimpses into the most powerful processes shaping the lives of compact stars. Stellar nurseries shape the spiral arms. The Milky Way's spiral arms are not simply made of stars, they're woven from the birthplaces of stars. Giant clouds of hydrogen, dust, and molecules drift through the galaxy. And when these clouds pass through the spiral arms, they are compressed and set alight with newborn suns. These regions are called stellar nurseries, chaotic, glowing, and full of motion. Ultraviolet light from new stars lights up the clouds, painting the arms with radiant blues and silvers. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star, even the Sun, was born from one of these cloudy cradles long ago. The Milky Way is surrounded by a vast halo. Beyond the flat spiral disk lies something far more diffuse, a spherical halo that surrounds the entire galaxy. It contains ancient stars, globular clusters, and enormous amounts of dark matter. Though it is nearly invisible, this halo may hold the majority of the Milky Way's mass. Its stars are spread thin across vast distances, orbiting in long, slow arcs that rarely touch the disk. The halo also preserves the remnants of ancient galactic mergers, streams and shells of stars torn from smaller galaxies and left behind like cosmic fossils. It is the galaxy's outer memory, quiet and dim, but still in motion, still shaping what the Milky Way becomes. It contains over 150 globular clusters. Globular clusters are among the oldest objects in the galaxy, compact spheres made of hundreds of thousands of tightly bound stars. They orbit the galactic center in the halo, like moths circling a distant flame. These clusters are incredibly stable, some more than 12 billion years old, and many contain stars that predate the Milky Way itself. Their stars are metal-poor, meaning they formed before the universe had time to create many of the heavier elements. They serve as time capsules, holding clues to how the galaxy formed, what it consumed, and what conditions were like in the early cosmos. These quiet golden spheres drift patiently above and below the galactic plane, glowing in the dark. The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. Even now, it continues to gather material, gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that feed its halo. It grows not like a living thing, but like a gravitational structure deepening over time. Some of this growth happens quietly, through infilling clouds. Other times, it comes with disruption, as satellite galaxies are torn apart and their stars scattered across the sky. The galaxy you live in today is not the same one the dinosaurs saw, and the one your distant descendants may know could be larger still, stitched from the ruins of 1,000 smaller worlds. Some planets orbit dead stars. Although it may seem unlikely, planets can survive the dramatic transformation of a star into a stellar remnant. Some orbit white dwarfs, the hot cores left over after stars like the Sun shed their outer layers. Others circle neutron stars, which form from the collapse of massive stars. These environments are harsh, flooded with intense radiation, yet some planets endure. They may have formed after the star's death, assembling from leftover debris, or they may have migrated inward over time. Around white dwarfs, a planet can receive stable light and heat once the remnant cools enough. Around neutron stars, conditions can be extreme, with strong magnetic fields influencing the planet's atmosphere. The presence of planets around dead stars challenges assumptions about planetary survival. It shows that worlds can persist even after dramatic cosmic events. These planets offer insights into how systems rebuild themselves and how diverse planetary environments can be. They serve as reminders that even the aftermath of stellar death can give rise to new and surprising structures. The galaxy contains regions rich with organic molecules. Across the Milky Way are clouds filled with complex organic molecules. These molecules form on the surfaces of dust grains or within cold gas, combining simple elements into intricate structures. Some of these molecules are precursors to the chemistry found in living organisms, although their presence does not imply life. Instead, they show that the building blocks of biology can arise naturally in many environments. These regions are often located in dense molecular clouds where temperatures are low and ultraviolet radiation is limited. Infrared and radio telescopes detect the signatures of these molecules, revealing their abundance. Their presence suggests that chemistry in the galaxy is rich and varied. Understanding how these molecules form helps astronomers learn about the early stages of planetary development. They may eventually become part of comets, asteroids, or even planets. The idea that organic complexity exists in quiet clouds scattered throughout the Milky Way brings a sense of connection to the broader universe. It shows that the seeds of chemistry are widespread, waiting for the right conditions to unfold. The galaxy has enormous molecular clouds. Scattered throughout the Milky Way are vast, dark clouds of cold gas, the raw material of stars. These molecular clouds, composed mostly of hydrogen molecules and traces of dust, can span hundreds of light years across. Within their cold, dense interiors, gravity begins to gather material, forming clumps that collapse into new stars and planets. Some of these clouds are so large and so cold, but they absorb visible light entirely, appearing as black patches against the starry sky. They are the galaxy's wombs, quiet, hidden places where the future begins in silence, tucked within curtains of shadow and gas. Supernova stir the galaxy like storms. When massive stars reach the end of their lives, they explode in cataclysmic supernova, events so powerful they can outshine entire galaxies for a brief moment. These explosions don't just end lives they create. Shockwaves from supernova ripple through the interstellar medium, compressing nearby clouds and triggering new waves of star formation. They enrich the surrounding space with heavy elements like iron and gold, forged in the heart of the dying star. In this way, supernova act like storms within the galactic ecosystem, stirring, fertilizing, and reshaping everything around them. They are the galaxy's moments of chaos, destructive, radiant, and necessary. There are worlds locked in perpetual twilight between their suns. In some binary star systems, a planet can settle into an orbit that places it between two stars in a balanced configuration. When this happens, the combined light from the pair can create a world bathed in constant twilight. The sky would never become fully dark, and true day might never arrive. The lighting on such worlds would shift softly as the stars move in their own orbit, but darkness would remain rare. Temperatures on these planets depend on the distance from the stars and the intensity of their light. Some of these twilight worlds may be mild, while others could be cold or even warm enough to allow liquid water. The gravitational forces from two stars create complex patterns in the planet's orbit, yet many of these configurations remain stable for long periods. Studying such systems shows how planetary environments can vary in surprising ways. They reveal that sunlight is not always simple or singular. These dusk-lit worlds offer a picture of planetary life shaped by soft and constant glow. Stellar nurseries in the Milky Way can spawn entire star clusters at once. Deep within the Milky Way lie vast regions of cold gas where new stars are born. These stellar nurseries often produce not just single stars, but entire clusters. As gravity pulls large quantities of gas together, the material breaks into many dense pockets. Each pocket can collapse into a star, leading to the formation of groups that emerge together. These clusters often contain stars of many different sizes, from massive blue giants to small red dwarfs. The stars interact through their gravity and radiation, shaping the environment around them. Young, massive stars create strong winds and intense light that carve out cavities in the surrounding gas. These processes can trigger additional star formation or halt it, depending on how the material is affected. Once the gas is cleared, the newly formed cluster begins to drift through the galaxy. Over time, some clusters remain intact while others slowly dissolve. Studying these nurseries reveals how the Milky Way continues to renew itself, building new generations of stars in waves of creation. Some stars shed their outer layers in vast shimmering shells. As certain stars near the end of their lives, they undergo changes that cause them to shed their outer layers. These layers expand into space, forming large, glowing shells of gas surrounding the dying star. The shells appear luminous because the remaining core heats the gas, causing it to emit soft light. These elegant structures are called planetary nebulae, although they have nothing to do with planets. Each one carries unique shapes formed by the star's rotation, magnetic fields, and the motion of surrounding material. Some nebulae form rings, others take on butterfly-like forms, and still others appear spherical. Over time, the gas disperses into the surrounding space, enriching the interstellar medium with elements created inside the star. These shimmering shells represent a brief but beautiful phase in the life cycle of low to medium mass stars. They provide vital clues about how stars evolve and how they contribute new material to the galaxy. Their delicate structures transform the quiet death of a star into a luminous event that ripples outward for thousands of years. The Milky Way contains strange carbon stars that burn with deep crimson light. Among the many stars in the galaxy, some shine with an unusually rich red color. These carbon stars have atmospheres filled with carbon compounds that absorb blue light and allow deep crimson tones to dominate. They form when aging stars dredge up carbon from their interiors and release it into their outer layers. This process changes the chemical balance of the atmosphere and gives the star its distinctive appearance. Carbon stars often appear especially bright in infrared wavelengths, making them stand out in surveys of the galaxy. They also produce dust that enriches the interstellar medium. Studying these stars helps astronomers understand how elements are cycled through stellar evolution. Their red glow adds diversity to the Milky Way's population of stars, showing how different chemical processes can influence the appearance of starlight. These stars burn with a warm and gentle radiance, offering a reminder that even small changes in composition can create dramatic effects in the light we see. Some stars wander far from where they were born. A star's birthplace doesn't always define its destiny. Over time, many stars drift away from their natal clouds, pushed by gravitational interactions, orbital resonance, or the slow pull of spiral arms. Some stars are ejected at high speeds, flung across the disk or into the halo. Others migrate gradually, shifting their orbits inward or outward as they spiral through the galaxy. Even our Sun is not where it began. Tracing the paths of stars reveals a Milky Way that is anything but static, a galaxy alive with movement, exchange, and quiet dislocation. Home, for a star, may only be temporary. The galaxy's habitable zone may span tens of thousands of light-years. Just as Earth orbits in a Goldilocks zone around the Sun, not too hot or cold for life, the Milky Way may have its own galactic habitable zone. This region is thought to lie between the dangerous inner core, full of radiation and gravitational chaos, and the sparse, metal-poor outer edges, where planets may be harder to form. Somewhere in between lies a wide band where conditions are stable, star density is moderate, and elements like carbon, oxygen, and iron are abundant. Earth lies within this zone, one quiet orbit in a vast swirl where life might not be alone in finding a foothold. The spiral arms are not fixed structures. The Milky Way's spiral arms might seem like permanent features, grand, sweeping lines carved into the galaxy's disk. But they are not made of fixed stars. Instead, they are patterns, density waves, that ripple slowly through the disk, compressing gas and triggering new stars as they pass. Stars drift into these arms, shine for a while, and then drift out again. The spiral structure moves at a different speed than the stars themselves, like a traffic jam moving through a highway. From afar, it looks like form and order. From within, it's a pattern of shifting motion, held together by gravity and time, never still, always flowing. Massive supernova remnants still glow with fierce energy. When a massive star explodes, it leaves behind a cloud of gas and debris known as a supernova remnant. These remnants expand outward for thousands of years, interacting with the surrounding interstellar medium. Even long after the explosion has faded from view, the remnants continue to glow. Shockwaves heat the gas to high temperatures, producing X-rays and visible light. The filaments and knots within the remnant reveal details about the original star and the force of the explosion. Studying these remnants helps astronomers understand how heavy elements are dispersed throughout the Milky Way. They also show how energy from dying stars shapes nearby regions. Over time, the expanding remnant slows and cools, eventually blending into the surrounding gas. Yet during its active phase, it stands as a brilliant reminder of the dramatic events that occur when massive stars reach the ends of their lives. These glowing clouds show that the aftermath of a supernova remains vibrant and full of information long after the initial flash has faded. Some planets skim so close to their stars they glow red hot. In the Milky Way, there are planets that orbit so near their stars that their surfaces heat to extreme temperatures. These close-in worlds are often large and gaseous, with atmospheres that swell and shimmer under the intense radiation. The heat causes their clouds to glow, sometimes giving the entire planet a reddish or golden hue. Their dayside temperatures can vaporize minerals and metals, creating exotic atmospheric chemistry. The intense stellar winds constantly strip away particles from their upper layers, forming long tails of gas that trail behind them. These planets complete orbits quickly, sometimes in only a few days. Studying them reveals how planets adapt to being in such harsh proximity to their stars. Their structure, weather, and atmospheric escape provide valuable clues about planetary survival under extreme conditions. These red-hot worlds show that the Milky Way contains planets far stranger and more varied than the ones found in our solar system. Galaxies in the local group are gravitationally bound. Despite their vast separations, the galaxies of the local group are not drifting apart. In fact, many are moving slowly toward one another. Gravity holds them in a kind of slow-motion ballet, curving their paths across millions of years. Some of the smallest galaxies orbit the Milky Way like moons, looping and falling, dissolving into streams. Others drift independently, but remain tethered, caught in a web of shared motion. Over time, this group may condense. Galaxies may merge, fade, or be absorbed. It's not a static arrangement, but a gentle gathering of cosmic islands, a family drawn closer by time, inertia, and the long reach of gravity. The galaxy's disk has a thick and thin component. The Milky Way's disk looks flat from a distance, but up close, it's layered. The thin disk is where we live, a wide, dense plain filled with young stars, open clusters, and star-forming gas. But above and below it lies the thick disk, older, puffier, and more diffuse. Stars in the thick disk tend to be older, with fewer heavy elements. They move in orbits that are more tilted and elliptical, suggesting they formed under different conditions or were stirred by early galactic collisions. The galaxy's disk is not uniform. It's textured, layered, and shaped by time, like sediment settled on the floor of a cosmic ocean. The galaxy's magnetic field threads through the disk. Though invisible to the eye, the Milky Way is laced with a vast magnetic field, stretching across the disk, rising into the halo, and weaving through the interstellar medium. This field is weak by earthly standards, but over galactic distances, it shapes how cosmic rays travel, how gas clouds collapse, and how matter flows through space. It aligns with spiral arms, forms arcs above the plane, and twists into loops that defy simple explanation. Studying it requires radio telescopes and careful analysis, but its presence is unmistakable. The Milky Way does not just glow with light. It breathes with magnetism, a subtle pulse running through its bones. The interstellar medium is full of invisible structures. Between the stars lies more than emptiness. The interstellar medium, a thin blend of gas, dust, and plasma, weaves its way through the Milky Way like a fog. To the naked eye, it is mostly invisible. But when viewed with radio and infrared telescopes, it reveals a stunning complexity. It forms filaments, bubbles, shockwaves, and cold, dense clouds where stars are born. Supernova carve vast cavities in it. Stellar winds sculpt it into shapes that ripple across light years. The space between stars is not a void, but a shifting web of matter and magnetism, the quiet fabric from which galaxies evolve and life eventually begins. The Milky Way has stars that blast jets of particles across space. Certain stars in the galaxy produce narrow, powerful jets of particles that shoot outward at tremendous speeds. These jets often form when material spirals onto a dense object such as a neutron star or a young star surrounded by a disk of gas. As the material falls inward, magnetic fields twist and focus it into slender streams that leap into space. These jets can travel for long distances, sometimes reaching light years from their source. They illuminate surrounding gas, carving paths that reveal the structure of the region. In young stars, jets help clear away the leftover material from the formation process. In older, more compact stars, The jets can become extremely energetic, producing radiation detectable across the galaxy. These dramatic phenomena show how magnetic fields and gravity combine to create powerful and elegant structures. The sight of a star launching focused streams of energy into the dark is a reminder of how dynamic and creative the universe can be. Even small systems can produce effects that reach far beyond their immediate surroundings. A few stars move so fast they will escape our galaxy forever. Most stars in the Milky Way follow stable orbits shaped by the galaxy's mass. However, a rare group of stars travels at extraordinary speeds, fast enough to eventually leave the Milky Way entirely. These hypervelocity stars are launched by powerful gravitational interactions. Some are slingshotted by the central black hole when they pass too close. Others are released when their binary partners explode, suddenly freeing them from an orbit. Once accelerated, these stars move on long paths outward, eventually drifting into intergalactic space. They shine like ordinary stars but carry unusual velocities that reveal their dramatic histories. Studying them helps astronomers understand the extreme conditions near the galactic center and the outcomes of supernova explosions. These runaway stars remind us that even massive galaxies cannot hold all their members forever. Some will break free, carrying their light into the empty space between galaxies. Their journeys will last for billions of years, silent and solitary, shaped by the moment that set them on their way. Some regions in the Milky Way are filled with electric-sized plasma clouds. Scattered throughout the galaxy are clouds made not of cold gas, but of energized plasma. These regions contain charged particles that respond strongly to magnetic fields. As a result, they behave differently from ordinary gas clouds. They can twist into filaments, ripple like waves, or glow with soft light generated by electrons spiraling through magnetic structures. Many of these plasma clouds are created by massive stars or supernova explosions that pump energy into their surroundings. Others are shaped by turbulence in the interstellar medium. Studying these regions provides insight into the magnetic environment of the Milky Way, which cannot be observed directly. Plasma clouds help astronomers trace the invisible fields that thread the galaxy. They also influence how cosmic rays travel, guiding or deflecting them as they move. These charged regions add another layer of complexity to the Milky Way. They reveal that the spaces between stars are not empty, but filled with subtle energy, shaped by both matter and magnetic forces. Giant nebulae glow with colors created by energetic young stars. Throughout the Milky Way, there are vast nebulae lit by the presence of young, massive stars. These stars emit intense ultraviolet light that energizes the surrounding gas, causing it to shine with vivid colors. Hydrogen glows in soft reds, while oxygen can produce gentle greens or blues. These glowing clouds are often birthplaces of new stars. Inside them, dense pockets of gas collapse into young suns that eventually emerge from the surrounding material. The shapes of nebulae are sculpted by stellar winds, radiation, and turbulence, forming arches, pillars, and cavities that create some of the most striking scenes in the galaxy. Studying these nebulae helps astronomers understand how stars form and how they influence their environment. The glowing clouds also reveal the chemical makeup of the galaxy, since different elements produce different colors when energized. These luminous regions remind us that star birth is both powerful and beautiful. They fill the Milky Way with soft, colorful light, transforming ordinary gas into radiant sculptures shaped by the presence of young and energetic stars. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not fixed trails of stars. They are patterns, formed by waves of higher density, moving through the galactic disk. As gas and dust pass through these waves, they are compressed, triggering star formation and lighting up the arms with bright young stars. These stars eventually drift out of the wave, while new ones form behind them, creating a self-sustaining illusion of structure. Like ripples in a pond or traffic clumping on a highway, the arms are dynamic, always in motion. From a distance, they appear still. From within, they are a dance of matter and rhythm, shaped by gravity and time. Stars are born from cold, collapsing gas. In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light-years wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly takes hold. Small regions grow denser and begin to collapse under their own weight. As the gas falls inward, it heats, spins, and flattens, forming a protostar at the center. Over time, the pressure and temperature grow until nuclear fusion ignites and a new star is born. From the coldest shadows come the brightest lights, spun gently into being by the quiet force of gravity. Star clusters can dissolve into the galactic field. Many stars are born not in isolation, but in groups, tight clusters formed from the same collapsing gas cloud. These clusters, bound by mutual gravity, drift together for millions or even billions of years. But over time, they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away one by one until the cluster fades into the general star field of the galaxy. Even our Sun was likely born in a stellar cluster long ago, its siblings now scattered, dimmed, or lost in the haze of distance. The galaxy contains ancient hypermetal-poor stars. Among the rarest and most precious objects in the Milky Way are hypermetal-poor stars, stars whose atmospheres contain almost no elements heavier than helium. Some of these contain less than 1/10,000th the iron found in the Sun. These stars are believed to be among the first born after the very first supernova, carrying only faint traces of enrichment from a universe still forming itself. They are incredibly old, incredibly pure, and scattered in the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing, gravitationally bound signature from a near-forgotten epoch. Some stars in our galaxy rotate with blinding beams like cosmic lighthouses. There are stars called pulsars that rotate quickly and emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space. When the beam points toward Earth, we see a pulse of light that repeats with remarkable precision. The effect is similar to a lighthouse turning in the night, though far more powerful. Pulsars are created when massive stars collapse into neutron stars after supernovas. Their rapid rotation and intense magnetic fields make them unique among stellar remnants. Some pulsars spin several times per second, while others rotate hundreds of times in that span. Their steady pulses help astronomers measure distances, map regions of the galaxy, and study fundamental physics. Pulsars reveal how matter behaves when compressed to incredible densities. They also contribute to our understanding of gravitational waves, since pairs of pulsars orbiting each other can produce ripples in space-time. These cosmic lighthouses add rhythm to the Milky Way, sending steady signals through the darkness that allow us to study far-off regions with surprising clarity. Certain regions glow with radiation from past cataclysms. Throughout the Milky Way, there are zones that emit faint but persistent radiation. This glow is the lingering energy left behind by ancient events such as supernovas, gamma-ray bursts, or interactions between dense clouds of gas and high-energy particles. These regions may no longer contain the original sources of the disturbance, yet the radiation remains as a signature of past activity. The glow often appears in wavelengths invisible to human eyes, such as X-rays or gamma rays. Observing these regions allows astronomers to uncover the hidden history of the galaxy. They reveal areas where powerful events once occurred, shaping the surrounding environment. Some of the radiation comes from electrons spiraling through magnetic fields or from gas heated to extraordinary temperatures. These glowing zones serve as reminders that the galaxy has experienced many energetic episodes. Even though the original explosions may have happened long before humans existed, their echoes still travel through space. This quiet radiation tells stories of enormous forces that once stirred the Milky Way, leaving behind traces that linger for millions of years. At the galactic center, clouds move with speeds that defy intuition. Near the heart of the Milky Way, clouds of gas behave in ways that seem almost unreal. These clouds orbit close to the central black hole, where gravity becomes incredibly strong. As a result, they move with speeds that are difficult to imagine. Some clouds race around the center at hundreds of kilometers each second, tracing elongated loops shaped by the uneven distribution of mass in the region. The environment here is dense with radiation, magnetic fields, and swirling stars. These factors create turbulence that twists and stretches the clouds into strange shapes. Observing them requires infrared and radio telescopes because thick layers of dust block visible light. When scientists track their movement, they see gas rushing, colliding, and flowing in spirals that reveal the invisible structure of the core. These rapid motions also help astronomers estimate the mass of the central black hole by showing how strongly the region pulls on its surroundings. The pace and energy of this environment contrast sharply with the calm appearance of the night sky. Deep inside the Milky Way, the clouds dance at unimaginable speeds, shaped by forces far stronger than anything found near Earth. Some worlds orbit their stars in minutes instead of years. Not all planets follow slow, sweeping orbits like the ones we know in our solar system. In the Milky Way, there are worlds that circle their stars so closely that they complete an orbit in minutes. These ultra-short period planets hug their stars so tightly that the side facing the star becomes incredibly hot, while the far side remains much cooler. Their paths are shaped by intense gravity and fierce radiation that constantly pulls at their atmospheres. Many of these worlds may have lost much of their original material, leaving behind dense, rocky cores. Their proximity to their stars means that they move at extraordinary speeds, sometimes traveling tens of kilometers each second. Studying these planets helps scientists understand how worlds evolve under extreme conditions. They reveal how orbits shrink over time and how planets adapt to intense heat. These rapid orbits also create unusual cycles of day and night. The idea of a year lasting only a few minutes challenges our sense of planetary motion and highlights the incredible variety of systems that exist throughout the galaxy. There's more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat, luminous disk, but the majority of its mass resides elsewhere. The galaxy is surrounded by an enormous dark matter halo, extending far beyond the furthest stars. This halo holds the galaxy together, outweighing the disk by a large margin. It is populated sparsely with ancient stars and globular clusters, but its true bulk is unseen. When we think of the Milky Way, we picture its spiral arms and starry plane. But that's only the glowing surface. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything like a quiet shroud. The Milky Way's core may have flared as a quasar. Today, the heart of our galaxy appears quiet. But there is evidence that it was once dramatically more active. The presence of huge gamma-ray structures like the Fermi bubbles, and traces of high-energy light reflected in surrounding clouds, suggest that the supermassive black hole at the center may have once flared as a quasar, a brilliant, violent beacon fueled by infilling matter. Quasars are among the brightest objects in the universe, outshining entire galaxies. If the Milky Way once burned like this, it would have looked dramatically different, a spiral wrapped around a blinding heart of light. That time has passed, but the echoes remain. The galaxy's structure changes over billions of years. Galaxies may look timeless, but they are always evolving. Spiral arms shift, bars form and dissolve. Gas flows inward and outward. Stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and lopsided, is slowly altering. Encounters with dwarf galaxies and dark matter can bend or twist the structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is not the one that was, and not the one that will be. Its beauty lies not in permanence, but in quiet transformation. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide, black holes spiral together, neutron stars crash, and entire galaxies merge. These events send out gravitational waves, ripples in the fabric of space-time itself. Though faint, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel. They are incredibly difficult to detect, but observatories like LIGO and Virgo have already captured several. New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, as you rest, space itself is shifting. Not enough to feel, but enough to tell us that somewhere, far away, the universe is changing. Some planets in our galaxy orbit two suns at the same time. Across the Milky Way, there are planets that do not circle a single star, but move gracefully between two. These worlds orbit binary stars, following paths shaped by the combined pull of both suns. Depending on the distance between the stars, a planet may move around them together as if they were a single glowing center, or weave an orbit between them in a more complex pattern. Sunrises and sunsets on such worlds would be unlike anything imaginable on Earth. Sometimes both suns would rise at once. Other times one would set as the other climbed into the sky. The climate on these planets can be unusual, shaped by constant changes in heat and light. These systems reveal how flexible planetary formation can be. Instead of being disrupted by the presence of two stars, the surrounding disk of gas can still gather into planets that find stable paths. Studying these systems helps astronomers understand how planets adapt to different environments and how common these arrangements might be. The idea that entire worlds orbit twin suns adds a quiet sense of wonder to the Milky Way, showing that nature often builds more creative structures than we expect. Antimatter clouds hide near the galactic center. Deep near the center of the Milky Way lie traces of something rare and mysterious. Antimatter, a form of matter that behaves like an opposite twin to normal particles, appears in faint clouds in this energetic region. These clouds are not thick or bright, but their presence can be detected through the radiation produced when antimatter meets normal matter and annihilates. The origins of this antimatter are still being studied. It may come from the activity of massive stars, energetic jets near the central black hole, or interactions within dense clouds of gas. Because antimatter is difficult to produce and even harder to preserve, its presence in the galaxy is surprising. Studying these clouds helps scientists learn about the high-energy processes happening in the central region. It reveals conditions that cannot be recreated on Earth, where intense gravity, strong magnetic fields, and frequent stellar explosions combine. These subtle signals show that the center of the Milky Way is far from quiet. It is a place where unusual forms of energy gather, offering clues about the strange and powerful events that shape our galaxy's core. Long tidal streams reveal the ghosts of galaxies we once consumed. Stretching across the Milky Way are long, delicate trails of stars that drift through space like ghostly ribbons. These tidal streams are the remains of smaller galaxies that ventured too close to our own. Over millions of years, the Milky Way's gravity pulled them apart, scattering their stars along their former paths. Each stream carries the memory of a galaxy that once had its own shape and structure. By studying their motions and compositions, astronomers can trace the history of these lost companions. Some streams curve high above the galactic plane, while others flow through the spiral arms. Their shapes reveal how the Milky Way grows by absorbing smaller galaxies. These streams also map the distribution of dark matter, because their paths bend in response to invisible structures surrounding the galaxy. Tidal streams remind us that the Milky Way has a long and active past. It has interacted with many neighbors, each encounter leaving behind a faint and beautiful signature. These stellar remnants drift silently through the night, carrying stories older than Earth itself. Binary stars sometimes spiral together until they collide. In many parts of the Milky Way, stars form in pairs rather than alone. These binary stars circle each other in a gravitational dance that can last billions of years. Over time, some pairs slowly spiral inward. Their orbits shrink as they exchange energy through tides, stellar winds, or interactions with surrounding material. Eventually, the stars can grow close enough to merge. This collision produces an enormous burst of light and energy, sometimes creating a brief but spectacular event known as a luminous red nova. The merged star often becomes larger and brighter than either of its predecessors. Binary collisions help enrich the galaxy with heavy elements, because material is mixed and heated during the merger. Studying these dramatic unions helps astronomers understand how stars evolve and how certain rare objects are formed. Although the process takes an immense amount of time, the idea that two stars can slowly fall toward one another until they become one adds a poetic sense of motion to the Milky Way. Even in the calm night sky, quiet celestial dances are unfolding in ways we can only begin to imagine. Magnetic fields shape the flow of cosmic dust. Interstellar dust, tiny grains of carbon and silicate, moves not just under gravity, but also under the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave light. In others, they align with magnetic lines, polarizing the starlight that passes through them. Understanding these effects helps astronomers trace the magnetic field structure and even remove its influence from cosmic background studies. Dust is not passive. It dances to a magnetic rhythm, following hidden patterns in the dark. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a kilonova. In this brief, blinding explosion, enormous quantities of heavy elements are forged: gold, platinum, uranium, and more. These materials are cast into space, mixing with gas and eventually forming new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from such collisions. They are not just luminous bodies, but record keepers of ancient cataclysms, burning with the residue of stellar wreckage and cosmic alchemy. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies a bar of stars, an elongated bridge of light crossing the central bulge. But deep within that bar, astronomers have found hints of another, smaller bar, tilted at a different angle, rotating independently. This inner structure is difficult to see directly, obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. Bars like this may help funnel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The Milky Way's center is not one simple shape. It's a layered, shifting labyrinth of light and motion. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system. It draws in fresh gas from the intergalactic medium, long, tenuous streams flowing through the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter, shock-heated forms, lighting up in ultraviolet or X-ray light. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos. Some stars pulse in brightness like celestial heartbeats. There are stars in the Milky Way whose light rises and falls in rhythmic cycles. These pulsating stars expand and contract as their internal layers shift under the influence of heat and pressure. Each change in size alters the amount of light they emit, creating a pattern that can last hours, days, or months. The pulses act like heartbeats, revealing details about the star's interiors that cannot be seen directly. By studying the timing and strength of these pulses, astronomers can determine a star's mass, age, and temperature. Some of the most well-known pulsating stars are used as cosmic distance markers because their brightness patterns follow predictable rules. These stars help map the structure of the Milky Way by providing reliable measurements for distant regions. Pulsation can occur in young stars, aging giants, or stars in transitional stages of their lives. Each category has its own signature rhythm. The gentle flickering of these stars adds a quiet sense of movement to the galaxy, reminding us that even stable-looking points of light can contain complex rhythms deep within their glowing layers. Shockwaves from ancient supernovas still travel through the galaxy. Long after a supernova fades from view, the shockwave it created continues to move outward. These waves sweep through the Milky Way like expanding ripples, carrying the energy of the original explosion far across space. As they travel, they compress gas clouds, heat interstellar material, and leave subtle changes in their wake. Some shockwaves move through regions filled with dust, sculpting it into new shapes. Others pass through more empty areas, gradually weakening, yet still preserving the memory of their violent origins. These shockwaves can take tens of thousands of years to expand to their full size. Along the way, they can trigger new star formation by compressing cold regions of gas. They also enrich the interstellar medium with heavy elements created in the supernova. Modern telescopes can detect these shockwaves by observing the faint X-ray and radio emissions they produce. They appear as expanding shells or filaments that reveal the structure of the surrounding space. Even though the star that created them may be long gone, its influence continues to travel quietly through the galaxy, shaping the environment for future generations of stars. Dust in the Milky Way was forged in the final breaths of dying stars. The dust that fills the Milky Way has a dramatic origin. Much of it was created in the outer layers of aging stars as they reached the ends of their lives. As these stars expanded into red giants, their outer atmospheres cooled enough for tiny solid particles to form. When the stars shed their outer layers, these particles escaped into space. Other types of dust were created when massive stars exploded in supernovas, releasing freshly formed elements into the interstellar medium. Over time, dust grains drifted throughout the galaxy, becoming essential ingredients in the formation of new stars and planets. They help cool collapsing gas clouds, shield molecules from radiation, and provide surfaces on which chemical reactions can occur. Dust absorbs and scatters starlight, giving the Milky Way its soft glow and shaping the appearance of nebulae. Each grain carries the legacy of the star that created it. The thought that the dust in the galaxy, and even the dust that eventually formed Earth, came from the dying breaths of ancient stars, adds a gentle sense of connection to the larger cycles of cosmic life. A few stars orbit the galactic center with incredible speeds. Near the center of the Milky Way lies a region where gravity grows exceptionally strong. In this dense environment, a handful of stars orbit at extraordinary speeds, far faster than stars located in the more distant spiral arms. These rapid motions were first detected through careful tracking of each star's position over many years. Their tight, fast orbits provide compelling evidence for the presence of a supermassive black hole at the core of the galaxy. As these stars swing close to the center, they follow curved paths shaped by intense gravitational forces. Their motion allows astronomers to calculate the mass of the unseen object controlling their orbits. These stars also help reveal the structure of the central region, which is filled with complex clouds of gas, magnetic fields, and radiation. Despite the extreme conditions, the stars themselves are stable, shining quietly as they trace their dramatic paths. Observing them requires advanced infrared telescopes that can see through the thick dust surrounding the core. Their speed and precision offer rare insight into one of the most mysterious areas of the Milky Way, a place where space is warped by immense gravitational power. The Sun was likely born in a stellar cluster. Stars rarely form in solitude. They are usually born in groups, stellar clusters shaped from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of these. Long ago, it shared space with hundreds, perhaps thousands, of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the motion of the galaxy scattered the cluster. Most of the Sun's siblings have wandered far, flung into different orbits, carrying with them fragments of our shared past. Some may still shine nearby, invisible among the stars, lost family in a sea of light. The Sun's siblings are scattered across the galaxy. Though the Sun's birth cluster has long since dissolved, astronomers are searching for its lost siblings, stars that share its age, motion, and chemical fingerprint. Using vast surveys like Gaia and spectroscopic databases, researchers hope to identify these long-lost relatives. A few candidates have emerged, stars that may have shared our origin, formed from the same cloud of enriched gas. If found, they could reveal details about the conditions in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient kin may still shine. The galactic disk wobbles as it spins. The Milky Way's disk is not perfectly flat. It wobbles, gently rippling like a spinning plate nudged off balance. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly, like a vast wave moving through the stars. From Earth, we don't feel it. But from afar, the Milky Way is not a pristine spiral. It is a breathing, undulating sheet of stars, curving gently as it turns. Galactic tides can distort star clusters and streams. Just as the Moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters, clusters in the process of being unraveled, galaxies slowly torn apart. The galaxy doesn't break these structures suddenly. It unravels them patiently, strand by strand, over millions of years. Radio waves from the Milky Way reveal the echoes of exploding stars. Across the Milky Way, ancient explosions leave behind signals that travel farther than light from their shattered shells. These signals appear as radio waves, gentle in tone but powerful in reach. When a star dies in a supernova, the blast sends shock waves rippling through space. Those shock waves energize surrounding gas, causing it to glow in radio frequencies that can cross vast distances without fading quickly. Even long after the visible light of the explosion has dimmed, the radio glow remains, drifting quietly through the galaxy. Astronomers use sensitive instruments to trace these faint echoes, mapping the structure of old remnants hidden inside dusty regions. Each ripple carries information about the force of the explosion, the shape of the expanding cloud, and the materials released into space. These waves reveal the hidden history of stellar deaths that once enriched the galaxy with heavy elements. They allow us to study events far older than humanity, reaching into eras when entire regions of the Milky Way looked completely different. In this soft radio light, the galaxy speaks of its past, whispering memories of stars that lived brightly and ended in dramatic silence. A teaspoon of a neutron star would weigh more than a mountain. Neutron stars are among the densest objects in the universe, formed when massive stars collapse in on themselves after a supernova. Their matter becomes so tightly packed that ordinary atoms cannot survive. Protons and electrons merge into neutrons, creating a substance unlike anything on Earth. If you could take a teaspoon of this material, something no human could ever actually do, it would outweigh a mountain. This unimaginable density reshapes the way light, magnetism, and gravity behave nearby. Neutron stars can spin rapidly, sending beams of radiation sweeping across space. They also generate magnetic fields far stronger than anything produced by human technology. Their surfaces are incredibly smooth, with gravity so intense that even a small bump cannot exist for long. These strange remnants cool slowly over millions of years, gradually fading as they release trapped heat. Studying them helps scientists understand the limits of matter and the conditions that exist in extreme environments. The thought that so much mass can be compressed into such a tiny space inspires a deep sense of wonder. Neutron stars remind us that the universe holds states of matter far beyond everyday experience. The Milky Way contains star streams that stretch across the sky like ancient rivers. Throughout the galaxy, long chains of stars drift together along gentle arcs. These star streams are the remains of smaller galaxies and clusters that were once whole but slowly pulled apart by the Milky Way's gravity. As they were stretched, their stars scattered along their original orbits, forming sweeping trails that can span great distances. Although faint, these streams act as records of the Milky Way's past interactions. By studying their shapes and motions, astronomers can reconstruct the histories of the galaxies that contributed them. Some streams curve high above the galactic disk, while others flow quietly within it. They reveal how gravity sculpts the structure of the Milky Way over time, redistributing stars across enormous scales. These delicate ribbons also help scientists map the invisible dark matter halo surrounding the galaxy. The paths of the stars trace the gravitational field, allowing researchers to understand how unseen mass shapes their motion. In a quiet way, star streams show that the Milky Way is constantly evolving. They carry memories of ancient encounters, stretched across the sky like soft reminders of the galaxy's long and complicated history. New stars ignite in our galaxy every single second. Across the Milky Way, star formation never truly stops. In cold and shadowed clouds scattered throughout the spiral arms, new stars emerge as gravity pulls gas together into dense pockets. These pockets slowly compress until temperatures rise high enough for nuclear fusion to begin. That moment marks the birth of a star. Although it may seem incredible, this process happens so often across the vast disk of the galaxy that new stars ignite every second. Some are tiny red dwarfs that will burn quietly for trillions of years. Others are larger and brighter, destined to live fast and end in powerful supernovas. The locations where star formation occurs are shaped by turbulence, magnetic fields, and the leftover material from older generations of stars. Light from newly formed stars gradually clears surrounding dust, revealing clusters that shine against the darker background. These young stars also influence their environment by sending out energetic winds, sculpting the clouds that created them. The continuous birth of stars is one of the processes that keeps the Milky Way alive and dynamic. It ensures that even as older stars fade, new sources of light are always appearing. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, but occasionally, a star reaches escape velocity, over 500 kilometers per second, and is flung outward, never to return. These hypervelocity stars are rare, but real. Some are thought to be ejected by interactions with the supermassive black hole at the galaxy's center. Others may be slingshotted by three-body encounters or supernova in binary systems. Once free, they travel alone into intergalactic space, tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the great dark between galaxies. The Milky Way contains stars fro other galaxies. Not all stars within the Milky Way were born here. Some may have originated in other galaxies, captured during mergers or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits, far from the disk, tracing paths through the outskirts or halo. They can be identified by their composition or motion, stars that don't quite fit the local patterns. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system, it is a living mosaic, slowly stitched together by time and motion. There's a fountain of gas cycling between the disk and halo. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernova and stellar winds heat and eject material upward into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy, in this way, doesn't just spin. It circulates, it exhales and inhales, keeping its structure in motion across immense spans of time. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Though not alive, they are chemically rich, formed in the atmospheres of dying stars or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not just debris, it is a cargo of potential, drifting silently through the dark. The sun races through the Milky Way faster than a bullet. We often think of the sun as steady and still, a warm and familiar anchor in the sky. Yet in reality, it is hurtling through the galaxy at a speed far beyond anything we can experience on Earth. It moves faster than a bullet, sweeping our entire solar system along with it. Everything you know, every planet, every moon, every drifting speck of dust is riding this grand motion. The Sun follows a curved path around the center of the galaxy, guided by gravity and shaped by the mass of countless stars. Even though we cannot feel this motion, it is always happening. It shapes the long future of our solar system and determines how we drift through different regions of the Milky Way. As the Sun journeys on, it encounters clouds of gas, faint radiation fields, and shifting gravitational currents that subtly influence the space around us. This silent voyage has lasted for billions of years and will continue for billions more. The thought that our familiar star is actually a traveler in an enormous galactic orbit invites a quiet sense of awe. We are passengers on a journey that never stops. Stars are born in clouds so cold, but fire cannot form there. When most people imagine star birth, they picture heat, flames, and blazing energy. The truth is far stranger. Stars begin in clouds that are colder than anything on Earth, so cold that fire is impossible. These clouds are made of dust and gas drifting through the Milky Way. They look dark to our eyes because they block starlight. Inside them, temperature drops to levels where molecules move slowly and gently. Gravity does the work that fire cannot. It gathers the cold material, pulling it together until it forms dense pockets. As these pockets grow heavier, they contract even more. Slowly, through pressure alone, the center begins to warm. Over long stretches of time, the temperature climbs, and only when it becomes incredibly high does nuclear fusion finally ignite. That moment transforms a silent, cold cloud into a shining star. The idea that brilliant suns begin as chilled, shadowed knots of dust feels almost like a cosmic secret. It tells us that creation often begins in stillness. Before any light appears, the galaxy forms its stars in quiet places where heat is only a distant dream. Our solar system floats in a giant bubble carved by ancient stellar explosions. We live inside a vast cavity in space without ever noticing it. Long before humans existed, powerful stars near our region of the galaxy lived fast lives and ended in explosive deaths. Those explosions pushed away enormous amounts of gas, clearing out a wide area. The result is a giant bubble that surrounds our solar system. This bubble is filled with thin, hot gas created by the shock waves of ancient supernovas. The material here is far less dense than the gas found elsewhere in the Milky Way. Our Sun and planets drift comfortably within this airy region, moving through it as if passing through a quiet room left behind by violent events. The edges of the bubble are shaped like walls of cooler gas where the remnants of those explosions finally slowed down. Astronomers can map this structure by tracing the faint light emitted by the gas inside it. Realizing that our entire solar system sits within the remains of long-vanished stellar giants brings a soft and humbling perspective. We are surrounded by the quiet echo of ancient cosmic events that shape the space we now call home. The Milky Way is slowly consuming smaller galaxies. Galaxies may look peaceful from a distance, but they are dynamic structures that interact and merge over long stretches of time. The Milky Way is no exception. It is slowly drawing in several smaller galaxies that orbit nearby. Their stars are stretched into long streams that wrap around our galaxy like faint ribbons. These streams reveal the paths of the smaller galaxies as they are gradually torn apart. Gravity pulls them in, bit by bit, until their stars become part of the Milky Way itself. This process has happened many times in the past, and it will continue far into the future. It helps explain the presence of old star clusters and unusual stellar populations scattered throughout the galaxy. The Milky Way grows through these ancient mergers, absorbing the remains of smaller companions. Even now, faint galaxies like the Sagittarius dwarf are being pulled apart as they fall inward. The idea that our galaxy is shaped by a long history of gentle and relentless cannibalism feels both strange and fascinating. It reminds us that even structures as vast as galaxies are still influenced by the quiet pull of gravity. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels. They are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see, it extends deep into the dark, shaped by wanderers at its edge. The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided. One side of the disk is thicker than the other. The spiral arms are uneven in brightness and extent. Even the stellar halo is slightly off-center. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, with dark matter clumps, or with past mergers. The galaxy is not a perfect pinwheel. It is a living structure, marked by tugs and twists, like a spinning dancer whose skirt has been caught by the wind. Its beauty lies in that irregularity, a graceful imbalance, sculpted by time. Astronomers map the galaxy using variable stars. Certain stars pulsing brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types, like Cepheids and RR Lyrae, have well-known relationships between their brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and, by comparing that to how bright it appears, its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion through time. It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the Sun's orbit with exquisite detail. With each new data release, Gaia deepens our understanding, turning a hazy smear of stars into a sharp, living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. Our galaxy is so vast that light needs 100,000 years to cross it. When you imagine light, you might picture something impossibly fast. It slips across a room in an instant and touches your eyes before you even notice it has moved. Yet when that same light tries to cross the Milky Way, it becomes almost slow in comparison. It would take it 100,000 years to go from one end of our galaxy to the other. That distance is so enormous that it stretches the imagination. The space between the stars is not empty, but it is open enough that light travels freely through it, brushing past dust grains and drifting atoms. The sheer scale means that when we look deep into the Milky Way, we are not seeing it as it is now. We are seeing layers of history stacked across unimaginable distances. The light from distant regions began its journey long before any human being existed. Every faint shimmer in the sky carries a fragment of ancient time. It reminds us that even the fastest thing in the universe becomes gentle and patient when measured against the size of our cosmic home. A supermassive black hole sits at our center, with a grip strong enough to bend space. Deep in the heart of the Milky Way lies something that cannot be seen directly, yet its presence shapes the entire galaxy. A supermassive black hole waits there, hidden behind clouds of dust and stars that whirl around it at incredible speeds. Its gravity is so intense that it bends the very structure of space. Stars near the center trace looping paths that reveal the invisible mass guiding their motion. At great distances, its influence is gentle, but close to the core, it becomes overwhelming. Gas clouds stretch and twist as they fall inward, heating up and glowing as they spiral toward the dark center. Although the black hole itself is silent, the region around it pulses with activity created by matter rushing into its grasp. This hidden heart anchors the Milky Way, giving shape to its rotation and helping bind its stars together. Imagining something so powerful and yet so quiet, something that can bend space without light or sound, invites a deep sense of wonder. The center of our galaxy is not a calm place, but a restless zone ruled by an unseen giant. The Milky Way once swallowed a galaxy nearly half its size. In the deep past, a large companion galaxy drifted too close to the Milky Way and was gradually pulled apart by powerful tides. Its stars, star clusters, and streams of debris were absorbed into the halo, becoming part of the structure we see today. Evidence of this ancient feast appears in the form of unusually energetic stars and broad sweeping arcs of stellar material that trace the remains of the lost system. Astronomers can still identify these fragments by studying their motion and chemical fingerprints, which differ from those of stars born within the Milky Way. This event may have thickened the galactic disk, stirred its dark matter halo, and influenced the development of the spiral arms. It stands as a reminder that galaxies grow through acts of cosmic consumption, absorbing entire systems over immense stretches of time. The Milky Way we know carries within it the remnants of this vanished giant, a ghostly companion whose stars now shine as part of our own celestial home. Our galaxy is surrounded by dozens of ancient satellite galaxies. Encircling the Milky Way is a quiet community of smaller galaxies, each one carrying memories of a much earlier universe. These companions drift in long, graceful orbits, some so faint that they blend almost completely into the dark around them. Their stars are often old and lightly populated, giving them a fragile appearance, yet they play an important role in the Milky Way's evolution. Their slow passages tug at our galaxy's outer halo, stirring subtle waves that ripple through the dark matter envelope. Some have already begun to shed delicate streams of stars, leaving pale trails that wrap around the Milky Way like ancient threads. Studying these companions reveals how large galaxies grow, not through sudden events, but through countless gentle interactions spread across unimaginable spans of time. They move like elders around a great family, each one preserving a chapter of cosmic history that deepens our understanding of how the Milky Way became the spiral we know today. The galactic plane marks a dense path of stars. If you look up on a dark night, away from city lights, you may see a hazy river of starlight crossing the sky. That's the galactic plane, the thickest slice of the Milky Way's disk. It's not a line, but a depth, a vast flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we're looking along the grain of the galaxy, peering through its richest corridors. This band isn't just beautiful, it's the crowded, humming heart of where most stars live and die. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we can't see the very center in visible light. Dust clouds obscure our view, but the area glows with brightness in infrared and radio. Even with the naked eye, the region appears more crowded, more luminous, filled with the overlapping light of billions of stars. We orbit far from the center, in a quiet suburb of the galactic disk. But when we look inward, we glimpse the crowded city at the galaxy's heart. We see the Milky Way John from Earth. Because we live within it, we cannot look down on the Milky Way from above. Instead, we see it from the inside, a flat ribbon of stars stretching across the sky, curved only by the horizon. This John view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the spiral we belong to. From Earth, we gaze through its disk, like standing in a forest and looking along the line of the trees. We do not see the shape we're part of, only the vastness that surrounds us. The galaxy holds far more than we can ever possibly see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outnumbers luminous stars. Between every star lies emptiness, and within every empty space, potential. The Milky Way is not just what we see, it is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, floating through a story too wide for the eye. Some stars here are more than twice as old as Earth. The Milky Way holds stars that formed long before Earth ever existed. Some of them are more than twice as old as our planet. These ancient stars provide a glimpse into the early days of the galaxy. They carry chemical signatures that reveal what the universe was like shortly after the first generations of stars lived and died. Old stars contain fewer heavy elements because those elements had not yet been created in large amounts by earlier supernovas. Their light is different, their atmospheres simpler, and their stories longer. Many of these stars drift in the galactic halo, a sparse region surrounding the Milky Way. They move on orbits that take them high above the spiral arms. Observing them allows astronomers to study the early universe in a quiet and direct way. These ancient suns burned steadily, holding secrets from a time when the galaxy was still new. Their existence adds a deep sense of continuity, a reminder that long before our world formed, the Milky Way was already shining with the light of its earliest stars. The galaxy glows with light from stars too faint for any telescope to see. When we look at the Milky Way on a clear night, we see a glowing band stretching across the sky. Much of that glow comes from stars so faint that not even powerful telescopes can pick them out individually. These stars are small and dim, but they are incredibly numerous. Their combined light forms a soft background that fills the disk of the galaxy. Dust and gas scatter this light, giving the Milky Way its hazy appearance. Even though these faint stars are individually invisible, they contribute significantly to the mass and structure of the galaxy. They help shape the gravitational pull that guides the motion of brighter stars. Some of them are old red dwarfs that burn slowly and quietly. Others are young stars just beginning their long lives. The idea that the galaxy shines with the collective breath of countless unseen suns creates a gentle feeling of mystery. The light we see is not just the glow of a few bright stars, but the soft chorus of multitudes that whisper across the sky. Rogue planets drift through the Milky Way without a sun. Not all planets belong to a star. Some worlds move freely through space, drifting alone through the darkness. These rogue planets were likely born in solar systems but were later cast out by gravitational interactions. Without a sun to warm them, they travel through the galaxy in deep cold. Their surfaces may be frozen, yet some could hide warm interiors powered by internal heat. The idea of planets wandering alone creates a haunting sense of quiet beauty. These worlds do not follow predictable orbits. They move on long paths shaped only by the gravity of the galaxy itself. They may pass near stars, slip through clusters, or disappear into the galactic halo. Although difficult to detect, their presence is predicted by simulations and hinted at by faint observations. There may be far more of them than planets that orbit stars. Thinking of these silent travelers drifting through the Milky Way invites a calm sense of wonder. In the vast dark spaces between the stars, entire worlds glide unseen, cold and solitary, carrying their own stories through the night. A halo of gas hotter than any flame on Earth surrounds our galaxy. Far beyond the spiral arms of the Milky Way lies a massive halo of extremely hot gas. This halo extends for great distances above and below the galactic disk. The gas within it is heated to temperatures far hotter than any flame found on Earth. It becomes so energized that it emits faint X-ray light. Although extremely thin, it contains enough mass to influence the motion of stars and satellite galaxies. This halo is thought to be a leftover from the early formation of the Milky Way, as well as the ongoing activity of supernovas that push material outward. It also acts as a reservoir of matter that may one day fall back into the galaxy, fueling new star formation. The halo is invisible to normal sight, yet it surrounds everything we know. It is a reminder that the Milky Way is not just a flat disk of stars, but a layered and intricate structure with components that stretch far into space. This hot, quiet atmosphere envelops our galaxy like a vast and ancient cloud. Interstellar clouds may seed solar systems with ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebulae. If that cloud contains water, carbon compounds, and other building blocks of biology, those ingredients may end up in comets, asteroids, or planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry. We don't yet know how common life is, but the conditions for it seem to arise naturally. The seeds of life may be scattered far and wide, tucked into the galaxy's coldest cradles, waiting for a place to grow. Some stars rotate hundreds of times faster than the sun. Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and unstable, with equators that bulge from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks around themselves. The sun rotates once every 25 to 35 days, depending on latitude. But these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark. The galaxy is tilted relative to the ecliptic. From Earth, the Milky Way arcs across the night sky in a graceful band of light. But it doesn't align with the plane of our solar system. The galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path traced by the sun and planets. This tilt is why the Milky Way rises at an angle and why it shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew, a small, tilted boat drifting through a larger, spinning sea of stars. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars, that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history etched into the outer halo. They have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back. Some stars spin so rapidly they would fly apart without gravity. In the Milky Way, there are stars that rotate with astonishing speed. Their equators can move at hundreds of kilometers per second, far faster than the rotation of our Sun. If not for the immense pull of their own gravity, these stars would tear themselves apart. Their rapid spin causes them to bulge outward, forming flattened shapes rather than perfect spheres. This distortion affects the temperature on their surfaces, making their poles hotter than their equators. The fast rotation can also lead to strong magnetic fields and affect how material flows around them. Some of these stars eject gas into surrounding space, creating disks or rings that glow softly. Their speed influences how they evolve over time, affecting how they burn their fuel and how they will eventually die. Observing them helps astronomers understand the limits of stellar physics, revealing how fast a star can spin before breaking. These rapid rotators offer a glimpse into a more extreme side of the Milky Way, where gravity and motion balance each other with delicate precision. They show that even stars can experience tension between stability and the forces that push them outward. Enormous cavities in the Milky Way hold vast amounts of empty space. Not all regions of the galaxy are filled with stars and gas. Some areas are surprisingly empty, carved out by ancient events that swept material away. These enormous cavities can span hundreds of light-years, leaving behind pockets of thin space inside the spiral arms. Many of them were created by clusters of massive stars whose intense winds and powerful supernovas pushed outward, clearing large sections of the surrounding medium. Over millions of years, these blasts hollowed out bubbles that merged into even larger voids. Although these regions contain fewer particles than their surroundings, they are still influenced by the gentle pressure of nearby gas and the gravitational pull of the galaxy. Studying these cavities helps astronomers understand how energy from dying stars shapes the Milky Way. They reveal where clusters once lived and how their activity influenced the surrounding environment. These vast pockets of emptiness contrast with the dense molecular clouds that form stars. They remind us that the galaxy is not uniform but shaped by cycles of creation and destruction that leave behind both bright birthplaces and quiet gaps in the starlit landscape. Diamond worlds exist deep in our galaxy. Among the many strange planets in the Milky Way, some worlds are thought to be rich in carbon to such an extent that their interiors may form diamond-like layers. These planets likely developed in regions where the materials available during their formation were different from those near our Sun. Instead of being dominated by silicates and metals, they contain high amounts of carbon that becomes compressed under intense pressure. In the deep interiors of these worlds, that pressure can turn carbon into solid crystalline structures similar to diamond. Their surfaces might be dark and rocky, but below lies a landscape shaped by exotic chemistry. These planets can orbit close to their stars or drift farther away, depending on how they formed. Studying them helps scientists understand the wide variety of conditions that exist across the galaxy. They show that planets can differ dramatically from those in our own solar system. Imagining entire worlds built from carbon-rich materials, with glittering layers hidden beneath their crusts, offers a quiet sense of wonder. These diamond worlds reveal that the Milky Way holds forms of planetary beauty far beyond anything we have seen on Earth. The Milky Way contains stars that release energy bursts powerful enough to scour planets. Some stars in our galaxy are capable of unleashing sudden bursts of energy that can dwarf the output of normal stellar activity. These bursts can occur when magnetic fields on the star's surface become twisted and then snap, releasing enormous amounts of radiation. The energy can be so strong that it would strip atmospheres from nearby planets or drastically alter their surfaces. These events are rare, but they show how unstable certain stars can be. The bursts travel through space as intense flashes of light and high-energy particles. Even from far distances, they can be detected by sensitive instruments. Studying these outbursts helps astronomers understand the magnetic behavior of stars and the environments around them. Many of these stars are young and still settling into stable patterns of rotation and energy output. Others are older but possess unusually strong magnetic fields. These sudden eruptions remind us that stars are not perfect spheres of calm light. They can be dynamic and unpredictable, sending out powerful pulses that reshape the space around them. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas, and even some stars, move in highly inclined orbits, passing above and below the galaxy's main structure. These polar orbits likely come from past mergers, when dwarf galaxies or stray clouds were captured at odd angles. Over time, they've continued to orbit on tilted paths, like comets around a planet. These misaligned orbits are records of disruption, visible reminders that the galaxy is not a closed system, but an evolving structure, shaped by the unpredictable flow of cosmic history. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. Over time, the expansion slows, but the shells remain, ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks, still echoing in the cold. Stars occasionally collide in dense regions. Space is vast, and stars are small. But in the densest regions of the Milky Way, such as the cores of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic. A burst of light, the merging of two suns, or the formation of a rare blue straggler star, one that appears younger than its neighbors. These collisions are rare, but not impossible. Over billions of years, the tightest stellar neighborhoods can rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently, and space is never quite empty. Binary stars can be torn apart by tidal forces. Many stars live in pairs, orbiting each other in gravitational embrace. But even this bond can be broken. If a binary system passes close to the Milky Way's central black hole, or through a dense cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star speeding through intergalactic space. These stellar breakups happen silently, in places we rarely see, a quiet tearing of ancient partnerships by gravity's indifferent hand. Some planetary systems boast dozens of worlds. While our solar system contains a modest number of planets, the Milky Way holds systems far more crowded. Some stars are orbited by dozens of planets, each following its own path through space. These systems form when large disks of gas and dust collapse around young stars. The material gathers into many clumps that grow into planets over time. Because the disks are large and dense, they can produce far more worlds than the one that gave rise to Earth. These planets can be small or large, icy or rocky, close to their star or drifting farther out. Their interactions create complex gravitational patterns that can shift over long periods. Studying these rich systems helps astronomers understand how planets form under different conditions. They show how varied planetary architecture can be, even within a single system. The idea that some stars host entire families of planets, far larger than our own, adds to the sense of abundance in the Milky Way. It suggests that the galaxy may hold endless varieties of worlds waiting to be discovered. Stars in the Milky Way can be kicked out of their homes and sent wandering alone. Not all stars remain where they were born. Some experience gravitational interaction so strong that they are flung out of their original systems. This can happen in crowded clusters where stars pass close to one another, or when a star's companion explodes in a supernova, abruptly altering the balance of forces. Once kicked away, these stars travel through the galaxy on long and solitary paths. They move faster than most stars, slipping through the spiral arms and drifting into quieter regions. Although they may appear ordinary in light, their motions reveal their unusual histories. Studying these runaway stars helps astronomers understand the dynamics of stellar systems and the forces that can disrupt them. These lone travelers offer a glimpse into the more chaotic moments of the galaxy's past. They show that even stars can be uprooted by powerful events, sent off on journeys that will take them far from their places of origin. Clusters in our galaxy hold stars packed so densely they blur together. In certain regions of the Milky Way, stars gather so tightly that the boundaries between them seem to vanish. These clusters form when large clouds of gas collapse into hundreds or even thousands of stars at once. Because they are born together, they remain close for long periods before slowly drifting apart. Inside these young clusters, stars can be separated by distances far smaller than the gaps between stars near our Sun. Their combined light blends into a brilliant glow that fills the sky from within. Some of these clusters are spherical, with stars packed densely toward the center. Others form loose associations that still shine brightly through the dust of the galaxy. Studying these clusters reveals details about stellar evolution, because the stars within them share similar ages but different masses. Observations show how stars change as they grow, age, and eventually fade. Clusters also play an important role in shaping their surroundings. Their powerful radiation and stellar winds carve out cavities in the surrounding gas, influencing where future stars will form. These crowded stellar communities remind us that many stars are born not in solitude, but in bright, bustling neighborhoods that glow with shared light. Molecular clouds here are massive enough to build thousands of suns. Across the Milky Way lie enormous molecular clouds, vast structures made mostly of hydrogen molecules mixed with dust. These clouds are some of the coldest and darkest places in the galaxy, yet they hold extraordinary potential. A single cloud can contain enough raw material to form thousands of stars the size of the Sun. Their immense mass allows gravity to shape them into dense knots where new stars take form. These knots collapse over time, igniting nuclear fusion deep within their cores. Despite their scale, molecular clouds are fragile in certain ways. Radiation from nearby massive stars can erode their surfaces, while shockwaves from supernovas can compress them, triggering new rounds of star formation. Many of these clouds stretch for hundreds of light years, winding through the spiral arms like shadowed highways of future starlight. They are essential to the ongoing life cycle of the galaxy, holding the ingredients for new solar systems. Observing them requires special instruments because they are opaque to visible light. Inside these dark cradles, entire clusters of stars wait to be born, hidden from view until their light grows strong enough to pierce the surrounding gas. The Milky Way's mass is still uncertain. You might think we would know the mass of our own galaxy, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast dark matter halo, which we cannot see directly. Estimates vary. Some suggest a mass close to 1 trillion times that of the Sun. Others place it much higher. The uncertainty comes from trying to measure how fast stars orbit at great distances, a task clouded by limited data and the influence of invisible matter. The Milky Way is our home, but its weight remains a quiet mystery. It may be heavier than Andromeda. For many years, astronomers assumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. But recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that's true, our galaxy could outweigh Andromeda, despite its more modest appearance. This matters not only for comparisons, but for predictions. When the two galaxies eventually merge, their relative masses will shape the encounter's dynamics. The Milky Way may look gentle, but beneath its quiet spiral arms, it carries more weight than we once imagined. The Magellanic Clouds may be on their first orbit. The large and small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way. But new evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity and motion through space hint that this could be their first close pass. If true, they're not long-standing companions, but distant wanderers just now falling under the Milky Way's pull. Their arrival has stirred the outer disk and warped the galaxy's shape, as if the Milky Way is responding to a new gravitational guest. The sky's quiet is full of first encounters. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas, a structure called the Magellanic Stream. It stretches over hundreds of thousands of light-years, wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces as the dwarf galaxies passed close to one another and to the Milky Way. Invisible in visible light, it reveals itself in radio wavelengths, a long, trailing whisper of motion and loss. The stream may one day feed new star formation in the Milky Way, or settle into the halo like a thread of memory stretching between galaxies. Gravity in some regions of the Milky Way warps the shape of starlight. As starlight travels through the galaxy, it can pass near regions of concentrated mass. These areas might be dense star clusters, dark matter structures, or even collections of gas that are more massive than they appear. When light moves through such areas, gravity bends its path slightly. This bending creates distortions that can magnify, stretch, or shift the appearance of distant objects. Astronomers call this effect gravitational lensing. In the Milky Way, lensing allows researchers to detect objects that are otherwise invisible, including planets drifting freely and compact stellar remnants hidden in dark areas. It also helps measure the distribution of mass in the galaxy, revealing how much is made of normal matter and how much is dark matter. The warping of starlight shows that the universe is not a flat or simple place. Even the light that reaches our eyes has been shaped by the landscape of gravity it traveled through. This quiet bending of light creates a sense of depth and complexity, reminding us that every view of the sky carries subtle traces of the invisible structures that fill the Milky Way. Cosmic rays from our galaxy strike Earth every moment. Throughout the Milky Way, high-energy particles are constantly accelerating through space. These particles, known as cosmic rays, come from supernovas, energetic stars, and turbulent magnetic fields. They travel at nearly the speed of light and move freely across vast distances. Even though Earth is protected by its atmosphere and magnetic field, a steady stream of cosmic rays reaches the planet at all times. Most of them are harmless, interacting with molecules in the upper atmosphere and creating showers of secondary particles that never reach the ground. Studying cosmic rays allows scientists to understand the energetic processes occurring throughout the galaxy. Their energies reveal information about the violent events that created them. They also help map magnetic fields, since the paths of cosmic rays bend as they move through space. Although invisible, their presence is constant, forming a quiet background of activity around our planet. Cosmic rays show that Earth is not isolated, but connected to the energetic workings of the galaxy. They provide a subtle reminder that the Milky Way is a dynamic environment filled with particles and forces that reach even our small world. Some stars are so hot they strip atmospheres from nearby planets. Certain stars in the Milky Way radiate such intense heat and ultraviolet light that they can gradually remove the atmospheres of planets orbiting too close. These stars are often young or unusually massive, burning brightly and releasing powerful winds of charged particles. When a planet is exposed to this constant flow of energy, its upper atmosphere begins to heat up and escape into space. Over long periods, the planet can lose much of its air, leaving behind a barren surface. This process helps shape the evolution of planetary systems. Some planets may begin with thick atmospheres but gradually become dry and airless. Observing these interactions allows astronomers to understand how stars influence the potential habitability of surrounding worlds. It also reveals how planetary atmospheres change over time in different environments. Even though the process is slow, the idea that a star's intense heat can reshape an entire planet adds a sense of power to the forces at work in the galaxy. These hot stars remind us that every world depends on the delicate balance between radiation, gravity, and the strength of its own atmosphere. The Milky Way contains magnetic monsters called magnetars. Among the rarest and most extreme objects in the galaxy are magnetars, a special type of neutron star with magnetic fields far stronger than anything found elsewhere. These fields are so intense that they can distort the structures of atoms and influence the surrounding space in unusual ways. Magnetars occasionally release bursts of energy that can briefly outshine all other stars in their vicinity. These bursts come from sudden shifts in the magnetic field, which cause the star's crust to crack. The resulting flare sends powerful radiation into space. Although magnetars are only a few kilometers across, their influence can be felt over great distances. They rotate slowly compared to other neutron stars, but their magnetic power makes them distinctive. Studying magnetars helps astronomers understand how matter behaves under extreme conditions. The existence of such objects adds a sense of mystery to the Milky Way, showing that even among neutron stars, there are rare and extraordinary members. Magnetars stand as reminders that the galaxy holds phenomena far beyond ordinary experience, where gravity, magnetism, and energy combine in dramatic and surprising ways. Hot gas bubbles form chimneys out of the disk. When clusters of massive stars go supernova, they create enormous cavities in the interstellar medium. These can join together into superbubbles, vast pockets of hot gas that punch upward through the galactic disk and vent into the halo. The result is a kind of chimney, a channel where energy, gas, and magnetic fields escape from the plane of the galaxy. These chimneys regulate the pressure of the interstellar medium, redistribute metals, and help shape the halo's structure. The galaxy, in this way, breathes, not just within the disk, but through towering columns that carry its energy up and out into the dark. The galaxy shines in X-rays from old stars and black holes, Though the Milky Way appears calm in visible light, it glows fiercely in other wavelengths. X-rays pour from its core, from collapsed stars, and from the edges of black holes. White dwarfs and neutron stars in binary systems can siphon matter from companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton. We cannot see this high-energy light with our eyes, but telescopes like Chandra and XMM Newton paint a very different portrait of the galaxy. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning, fast and precise, with beams of radiation sweeping across space. These are pulsars, and some rotate hundreds of times per second, pulsing in regular, measurable rhythms. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink quietly, remnants of death, but also beacons of astonishing order. They keep time not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in visible light, hidden by dust, distance, or faintness. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Using arrays of radio telescopes, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in darkness. While light is blocked, radio soundings let us see. The galaxy speaks in a language we can't hear, but one that science has learned to translate into shape and shadow. Some worlds experience metal or glass rain. Among the thousands of worlds in the Milky Way, some experience forms of weather entirely unlike anything on Earth. On certain hot exoplanets, temperatures soar so high that metals evaporate into vapor. When the atmosphere cools slightly, these vapors condense into droplets that fall as shimmering metallic rain. On other worlds, strong winds move molten droplets of silicate across the sky, creating storms of molten glass that whip sideways at tremendous speeds. The surfaces of such planets can be glowing oceans of lava, constantly reshaped by violent heat. These extreme conditions occur on worlds that orbit close to their stars or have unusual compositions. Their atmospheres reflect the intense radiation they receive, leading to weather patterns shaped by forces unknown on Earth. Observing these exotic climates helps astronomers understand the diversity of environments that planets can host. It reveals that weather in the galaxy is not limited to clouds and storms of water, but can include conditions that feel almost otherworldly. These metal and glass rains turn distant planets into shimmering, dangerous landscapes shaped by heat and alien winds. Repeated supernovas have carved enormous cavities in the Milky Way. Throughout the Milky Way, massive stars reach the ends of their lives in powerful explosions that send shockwaves into surrounding space. When many such explosions occur in the same region over millions of years, their combined energy can carve out enormous cavities. These cavities contain far less gas and dust than the areas around them. They appear as vast bubbles in the interstellar medium, shaped by overlapping shock fronts. Inside these spaces, the gas is often hot and thin, while the edges form denser walls where material has been swept aside. These structures reveal the history of star formation in their regions. Groups of massive stars tend to form together, live short lives, and explode within a relatively short span of time. Their collective activity reshapes the environment, influencing where new stars will appear. Studying these cavities helps astronomers understand how energy moves through the galaxy. It shows that the Milky Way is continually shaped by cycles of birth and destruction, each leaving its mark in the form of these vast hollowed-out regions. Stars exist in intergalactic space after being thrown out of the galaxy. Not all stars stay within the boundaries of the galaxies where they were born. Some are violently ejected during powerful gravitational interactions. When a star passes close to a black hole or a tightly bound cluster, it can gain enough speed to escape entirely. Once thrown free, it becomes a lonely traveler drifting through intergalactic space. These stars shine just like any other, but their isolation makes them incredibly difficult to detect. Their journeys may take them far from any source of light or warmth. The Milky Way has likely thrown out many such stars over its long history. Some were ejected during collisions with other galaxies. Others were cast away when their companions exploded, altering the balance of forces. Studying these runaway intergalactic stars helps astronomers understand the extreme events that can occur in galactic environments. They remind us that the universe is a place of motion and change, where even stars can be cast adrift. These solitary wanderers drift through the dark, carrying the story of the violent events that set them free. The Milky Way holds ancient star clusters older than any planet. Scattered throughout the galaxy are globular clusters, dense spheres of stars that formed when the Milky Way was still young. Many of these clusters are older than Earth, older than the Sun, and older than the planets in every known solar system. They contain some of the first generations of stars, created before the galaxy settled into its current spiral shape. The stars in these clusters move in tight orbits, packed closely enough to fill the night sky with light if viewed from within. Their chemistry reveals what the universe was like in its early stages, long before heavy elements became common. These clusters orbit outside the main disk of the Milky Way, drifting through the galactic halo on long, looping paths. Observing them helps scientists reconstruct the history of the galaxy and understand how its earliest structures formed. Their age gives them a quiet dignity. They have survived collisions, mergers, and countless cosmic events. They are ancient survivors floating through a galaxy that has changed dramatically since they first lit up billions of years ago. Some stars orbit in elongated, tilted paths. Not all stars move in neat circles around the galactic center. Some follow long, stretched ellipses, their paths looping high above and far below the disk, tilted at odd angles from the main plane. These stars likely come from different origins, relics of dwarf galaxies swallowed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits are clues, three-dimensional maps of the galaxy's chaotic past. By tracing their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems, tilted, stretched, but still bound to the whole. The Milky Way emits neutrinos we can barely detect every second. Trillions of neutrinos pass through your body, straight from the stars. These ghostly particles are produced in nuclear reactions, from the sun, from supernova, and from cosmic rays striking atoms in space. The Milky Way is bathed in them. Yet they are so light, so unreactive, that they slip through almost everything, leaving no trace. Special observatories, buried deep underground or under ice, try to catch just a few, flashes of light from a rare collision. Neutrinos carry information from places we cannot see, from stellar cores, collapsing giants, and the galaxy's unseen energy. They are the whispers of cosmic fire. Interstellar space isn't empty, it's a turbulent sea. Between the stars, space is not smooth or still. The interstellar medium, thin clouds of gas and dust, is stirred by shock waves, magnetic fields, and the motion of stars. Temperature can vary wildly. Flows of material collide, mix, and fragment. Clouds stretch, fold, and tumble. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are all affected by this restless sea. What looks from afar like calm starlight is, up close, a dynamic, rippling fabric, shaped by invisible winds and ancient energy. The galactic halo may contain rogue planets. Planets are not always tethered to stars. Some form normally and are later ejected from their systems. Others may never have had a star at all. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though difficult to detect, studies suggest that there may be billions of them in the Milky Way, some even in the outer halo, where stars are few and far between. Without light or warmth, they float unseen, warmed only by internal heat. They are orphans of the galaxy, planetary drifters following long, lonely paths through the darkness between stars. The Milky Way contains planets made almost entirely of water. Among the many worlds in our galaxy, some are believed to be dominated by water in forms not found on Earth. These planets contain vast quantities of water ice mixed with high-pressure liquids that behave differently from anything familiar. They may have thick atmospheres that trap heat, creating layers of superheated water deep beneath their clouds. Under intense pressure, water can take on exotic states that form dense crystalline structures. These planets are often larger than Earth, with strong gravity that holds their deep oceans in place. Some may have rocky cores buried beneath hundreds of kilometers of water. Observing them helps astronomers understand how planets form from different materials and under different temperatures. Their existence expands our idea of what a habitable world might look like. Instead of continents and oceans, these worlds could be global seas with no exposed land at all. Imagining entire planets shaped by water, yet entirely unlike Earth, brings a sense of quiet wonder to the Milky Way. They remind us that planetary diversity is far greater than we once believed. There are stars here so cool they could almost be mistaken for planets. Not every star in the Milky Way burns with fierce heat. Some stars are so cool and faint that their temperatures barely exceed those of giant planets. These ultra-cool dwarfs emit most of their light in infrared wavelengths, making them nearly invisible to the unaided eye. Despite their small size, they are still true stars, powered by steady nuclear fusion of hydrogen deep within their cores. Their low temperatures allow molecules to form in their atmospheres, creating complex patterns of light absorption. Studying these stars helps astronomers understand the lower limits of stellar formation. They also provide valuable clues about how planets might look when viewed from a distance. Some of these cool stars host their own planetary systems, where temperatures are gentle enough to allow a wide range of conditions. Because they shine so softly, life on planets orbiting them would experience a dim and reddish world. These cool stars remind us that the Milky Way contains many forms of starlight, from blazing giants to quiet, ember-like suns that blur the line between star and planet. The galaxy contains enormous arcs of gas that stretch for light years. Threaded through the Milky Way are immense arcs of gas that span incredible distances. These arcs are shaped by a mix of stellar winds, supernova explosions, and magnetic forces that push and pull the gas over time. Some arcs form curved walls around old cavities. Others trace long paths created by the motion of massive stars that drift through the interstellar medium. Because the gas is often thin and cold, it can be difficult to detect invisible light. Radio and infrared telescopes reveal its structure, showing delicate curves that stretch across hundreds of trillions of kilometers. These arcs help astronomers understand the history of star formation in their regions. Their shapes reveal past explosions, the flow of energy through the galaxy, and the way clouds respond to gravity and pressure. They act like enormous cosmic brushstrokes, marking areas where powerful forces once swept through. Seeing these shapes mapped across the Milky Way adds a sense of artistry to the galaxy, as if vast hands shaped its gas into beautiful curved forms. Some star clusters drift together through space for ages. Throughout the galaxy, groups of stars travel in harmony across great distances. These drifting clusters form when stars are born together within a single cloud of gas. Over time, gravitational interactions with other stars and clouds gently pull the cluster apart, yet many stars continue moving in the same general direction. These groups can persist for hundreds of millions of years, maintaining similar speeds and positions even as they spread out. Because the stars share a common origin, they have similar chemical compositions and ages. Studying these moving groups helps astronomers trace the history of star formation and understand how clusters dissolve over time. They also reveal how stars migrate through the galaxy, drifting from their birthplaces into new regions. Some moving groups eventually become so spread out that they blend into the background population of the Milky Way. Others remain coherent for long stretches, like quiet caravans traveling across the galactic landscape. Their gentle motion adds a sense of continuity to the Milky Way, showing how stars carry their shared beginnings with them as they drift. Planetary systems form throughout the Milky Way. Planets are not a rare feature of the cosmos. They are a natural consequence of star formation. As a new star ignites, a rotating disk of leftover gas and dust surrounds it. Within this disk, particles stick together, gather mass, and grow into worlds. Across the Milky Way, planetary systems are common. Some are vast, with gas giants and frozen moons. Others are compact, with rocky planets hugging close to dim stars. Some may resemble our own, while others defy our expectations entirely. The galaxy is not just full of stars. It is full of systems, solar families, each one with its own unique balance, orbit, and potential. Earth is near the co-rotation radius. In the Milky Way, the spiral arms rotate at a different speed than individual stars, like a moving pattern rather than a solid structure. But there is a special distance from the center, called the co-rotation radius, where the average speed of stars matches the rotation speed of the spiral arms themselves. Earth's sun orbits close to this boundary. This gentle match in motion may help us avoid frequent crossings of spiral arms, places with higher star density, more supernova, and gravitational disturbances. We live, quite possibly, in a more stable neighborhood of the galaxy, shielded not by walls, but by resonance. The sun bobs up and down through the galactic plane. As it orbits the Milky Way, the sun doesn't follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork in slow motion, rising and falling over tens of millions of years. This vertical oscillation is caused by the gravitational tug of the galaxy's mass, pulling and releasing the solar system as it moves. Some researchers have even wondered whether this motion might influence cycles of extinction on Earth, though the evidence is not yet clear. Still, it's a reminder. Even on its steady path around the center, the sun is not gliding, it's swaying, softly, through space. We don't know what dark matter is, but we know it's there. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly. It does not emit or absorb light. It passes through ordinary matter as if it weren't there. But its gravitational effects are unmistakable. It holds the galaxy together, explains the unexpected rotation speeds of stars, and shapes the formation of large-scale cosmic structures. Without it, the Milky Way would fly apart. Astronomers detect it not by seeing it, but by watching how it moves other things. It is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest mysteries in science. The galaxy holds hidden brown dwarfs that never became full stars. Brown dwarfs fill a quiet space between planets and stars. They form when clouds of gas collapse just as they would during star formation. But the resulting object never gathers enough mass to ignite full nuclear fusion in its core. Without this steady source of energy, brown dwarfs shine only faintly, glowing softly with leftover heat from their formation. They can have masses far greater than planets, yet remain too cool and dim to appear as stars. Because their light is weak and mostly emitted in infrared wavelengths, many remain unseen, drifting quietly through the Milky Way. These elusive objects help astronomers understand the lower limits of star formation. Their atmospheres contain unusual molecules shaped by cool temperatures and high pressure. Some brown dwarfs exhibit weather patterns that shift over hours or days, revealing dynamic behavior in their cloud layers. Although they do not burn like true stars, they play an important role in the galaxy's population. They fill the spaces between bright stars, adding hidden complexity to the Milky Way. Their gentle glow and mysterious nature offer a reminder, but not all celestial bodies fit neatly into familiar categories. Some worlds are covered in lava oceans. Certain exoplanets orbit so close to their stars that their surfaces melt into glowing seas of molten rock. These lava worlds are shaped by intense heat that prevents solid crust from forming. Instead, their surfaces churn with rivers of liquid stone that slowly flow under the pull of gravity and the motion of atmospheric winds. The temperatures on these planets can exceed the melting points of many minerals, turning their landscapes into luminous red and orange vistas. Some of these worlds also experience tidal forces from their stars, which cause their interiors to heat even more. As a result, volcanic activity can become widespread, feeding lava oceans that constantly renew themselves. Studying these extreme planets helps astronomers understand how worlds evolve under extreme radiation. Their atmospheres can contain vaporized rock that condenses into mineral clouds. When these clouds cool, they can produce unusual forms of precipitation that fall back into the molten surface. Lava worlds show that planetary environments in the galaxy vary far beyond anything seen on Earth. They offer a glimpse into cosmic landscapes forged by heat and motion in the harshest possible conditions. Pulsars in the Milky Way spin with the precision of cosmic clocks. Pulsars are rapidly rotating neutron stars that send beams of radiation out from their magnetic poles. Each time a beam sweeps past Earth, it produces a pulse of light that arrives with remarkable regularity. Some pulsars maintain timing so consistent that they rival atomic clocks in stability. This precision makes them valuable tools for studying the galaxy. By observing slight changes in pulse timing, astronomers can detect the influence of passing objects, gravitational waves, or movement within the pulsar itself. The rotation of a pulsar is a relic of the star that created it. When a massive star collapses, its core shrinks dramatically, causing it to spin faster in the same way a spinning ice skater speeds up when drawing in their arms. Although pulsars gradually slow over millions of years, their early stages can feature hundreds of rotations each second. Their intense magnetic fields guide charged particles along narrow paths, creating the beams that make them so distinctive. Pulsars serve as natural laboratories for extreme physics, revealing how matter behaves under conditions far beyond any experiment on Earth. The galactic center hides vast stores of molecular gas. Deep within the central regions of the Milky Way, lies an enormous reservoir of molecular gas. This material is dense, cold, and rich in the ingredients needed for star formation. However, the center of the galaxy is not a quiet or simple place. Strong radiation fields, turbulent motions, and intense gravity affect the gas constantly. Clouds are stretched, compressed, and heated as they orbit close to the central black hole. Despite the harsh environment, pockets of gas remain shielded enough for molecules to survive. These regions form some of the most massive and active star-forming sites in the galaxy. Observing them requires using radio and infrared wavelengths that can penetrate the thick dust surrounding the core. The distribution of this molecular gas helps astronomers understand how stars form under extreme conditions. It also reveals how energy moves through the galactic center, shaping the evolution of nearby regions. These hidden stores of gas play a crucial role in building new generations of stars, showing that even the most intense environments can be fertile grounds for creation. Cosmic rays constantly pass through us from the galaxy. Every second, high-energy particles, mostly protons and atomic nuclei, stream through your body, launched long ago by exploding stars. These are cosmic rays, and they are everywhere. They travel close to the speed of light, bending through magnetic fields, bouncing off clouds, and occasionally colliding with atoms in Earth's atmosphere, where they create showers of secondary particles. Most of the time, we don't notice them, but they carry stories from across the galaxy, evidence of ancient supernova, traces of distant acceleration, messages from the violent hearts of stars. Even as you rest, the galaxy is whispering, in particles, in silence, in lightless rays. The galaxy is not symmetrical. Though many diagrams show it as a neat, even spiral, the Milky Way is not perfectly balanced. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is lopsided. Even the star counts between hemispheres are slightly off. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living things, carry traces of their histories in their shapes, scars of collisions, wrinkles of time, and quirks of uneven growth that give them character and depth. The oldest known star may live in our halo. High above the galactic plane, drifting through the halo, astronomers discovered a star that may be nearly as old as the universe itself. It contains almost no heavy elements, a signature of stars born soon after the Big Bang, before generations of supernova enriched the cosmos. It likely formed over 13 billion years ago, long before the Milky Way was fully formed. It burns quietly now, with a soft red glow, low in mass but rich in history. It is not just a star. It is a time capsule, a living relic from the universe's earliest dawn. The center of the galaxy spins faster than the outskirts in the inner regions of the Milky Way. Stars orbit the center much more rapidly than those farther out. Near the core, the gravitational pull is stronger, packed with mass from stars, dust, and the supermassive black hole Sagittarius A*. This causes stars to sweep through tighter, faster orbits, completing revolutions in just a few million years. Out in the suburbs of the galaxy, like where our sun lives, stars orbit more slowly, taking hundreds of millions of years. This uneven rotation creates twisting patterns, stretches spiral arms, and keeps the disk from behaving like a solid structure. The galaxy moves like a great wheel, but one whose rim lags behind its core. The Milky Way contains clouds where ice crystals form in space. In the coldest regions of the galaxy, far from intense starlight, clouds of gas can become cold enough for molecules to freeze onto tiny dust grains. These frozen coatings form delicate ice crystals made of water, carbon dioxide, methane, and other compounds. These crystals play an important role in the chemistry of the interstellar medium. They provide surfaces where complex molecules can form, gradually building the raw materials that may one day contribute to planets or even life. Infrared observations reveal the presence of these ices by their distinctive absorption patterns. These frozen clouds appear dark, invisible light, hiding their treasures behind thick veils of dust. Studying them helps astronomers understand the earliest stages of star and planet formation. They show how cold and quiet the galaxy can become in its most sheltered corners. These icy environments act as gentle incubators where chemistry unfolds slowly over millions of years. Ancient red giants fill the galaxy with heavy elements. Red giants represent a late stage in the life of many stars. As they exhaust the hydrogen in their cores, they expand and cool, becoming large and luminous. Inside these vast envelopes, new elements are forged through nuclear reactions. Over time, red giants shed their outer layers, releasing these elements into the interstellar medium. This material becomes part of the gas and dust that will form new stars and planets. In this way, red giants enrich the galaxy with the building blocks for future generations of celestial bodies. Their slow and steady winds carry carbon, nitrogen, and other essential elements far into space. Observing red giants helps scientists understand the chemical evolution of the Milky Way. Their gentle glow and constant contribution to the cosmic cycle add a sense of continuity to the galaxy. They remind us that creation and renewal are woven into the life of every star, even those nearing the end of their luminous journey. Some stars wander on orbits that stretch across half the galaxy. Not all stars follow neat circular paths around the Milky Way. Some move on long, stretched orbits that carry them from one side of the galaxy to the other. These stars travel through regions with very different densities of gas, radiation, and gravitational pull. Their elongated paths often form when the stars originate in satellite galaxies that were later absorbed by the Milky Way. As these smaller galaxies broke apart, their stars were captured and set on wide-ranging orbits. Other stars may have been thrown into eccentric paths by close encounters with massive objects. Their journeys take them far above the galactic plane, then back down through the spiral arms. Observing these travelers allows astronomers to study the structure and mass of the galaxy on large scales. Their motions reveal how the Milky Way's gravitational field changes from one region to another. These wandering stars act as quiet messengers from the galaxy's past, carrying evidence of long-vanished mergers and ancient interactions. Their wide orbits show that the Milky Way is not a static disk, but a dynamic system shaped by countless events. The galactic halo contains faint stars that drift like cosmic ghosts. Surrounding the bright disk of the Milky Way is a vast halo filled with extremely old and faint stars. These stars drift through space with slow and steady motion, far from the bustling regions where new stars are born. Many of them formed in the earliest eras of the galaxy, before the spiral arms took shape. Their low brightness makes them difficult to detect, and their wide distribution means they are separated by great distances. These halo stars often have unusual chemical compositions, containing very small amounts of heavy elements. Studying them helps astronomers understand the conditions that existed shortly after the universe began forming stars. Some halo stars belong to ancient clusters that have survived for billions of years. Others were once part of smaller galaxies that merged with the Milky Way. Because the halo is so sparse, its stars appear isolated, shining quietly against the deep background of space. These drifting lights remind us of the Milky Way's earliest chapters, still present even after the galaxy has changed dramatically over time. There's a giant gamma ray bubble above and below the core. Stretching tens of thousands of light-years above and below the galactic center are two vast, ghostly lobes of high-energy light, the Fermi bubbles. Discovered only recently, they glow in gamma rays, extending like twin balloons from the Milky Way's heart. No one is entirely sure what caused them. They may be the remnants of a long-ago outburst from the central black hole, or the mark of fierce star formation that once flared through the core. Either way, these enormous structures drift silently over the galaxy, invisible to human eyes. They are reminders that the Milky Way has a past we cannot fully see, echoes of violence wrapped in radiance, far above the stars we know. We live in a minor spur between major arms. Our solar system doesn't lie in one of the Milky Way's grand spiral arms. Instead, we occupy a small structure called the Orion Spur, a relatively quiet lane of stars nestled between the larger Sagittarius and Perseus arms. It's not especially dense, nor especially active, but that may be why we're here. In the calm between galactic highways, massive supernovae are rarer, radiation storms less frequent. This quiet corner may have given life on Earth the time it needed to emerge and evolve. From the outskirts, the galaxy seems dramatic and radiant. But in this quiet spur, we've found just enough peace for complexity to unfold. The Milky Way has a bar-shaped center. When astronomers look toward the galactic core in infrared light, they see not a perfect circle, but a thick, elongated bar of stars crossing the middle, a kind of glowing bridge. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. Bars like this are common in spiral galaxies. They form when stars in the disk begin to drift inward and pile up along a central axis. Over time, the bar becomes a stable structure, stirring gas, triggering new stars, and feeding material toward the black hole at the center. It is not just a shape, but a dynamic engine, sculpting the galaxy's heart from within. It's part of a larger structure called the local group. The Milky Way doesn't exist in isolation. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster drifting together through space. The two largest members are the Milky Way and Andromeda, each with its own family of satellite galaxies. Scattered around them are smaller dwarfs, faint ellipticals, and star-poor galaxies made almost entirely of dark matter. The local group spans more than 10 million light-years, and it is bound together not by proximity alone, but by gravity. We are part of a family, quiet, widely spaced, but still linked by the invisible threads of shared motion and mutual pull. Some worlds are tidally locked and never see a sunrise. Many planets orbit their stars in such a way that the same side always faces the light. These tidally locked worlds have a permanent day side and a permanent night side. On the day side, temperatures can become extremely high, while the night side may be frozen in perpetual darkness. A narrow region between the two sides, known as the twilight zone, can maintain more moderate conditions. Atmospheres on these planets move heat around, shaping wind patterns and clouds in ways that differ from those on Earth. Some tidally locked worlds orbit small, cool stars where the habitable zone lies close to the star. Despite their unusual lighting, these planets may still be capable of supporting liquid water under the right conditions. Studying them helps astronomers understand how climates function when sunlight never shifts. Tidally locked worlds show the range of environments possible in the galaxy. They remind us that day and night, concepts familiar to us, can take on entirely different meanings elsewhere in the Milky Way. Giant bubbles of radio emission rise above the galactic center. Towering above and below the Milky Way's central region, are enormous bubbles that emit faint radio waves. These structures extend for thousands of light years and are filled with energized particles. The bubbles likely formed from past activity near the central black hole or from bursts of star formation that released vast amounts of energy. Their smooth outlines suggest powerful forces sculpted them, pushing gas outward into large lobes. Observing these bubbles helps astronomers understand the energetic history of the galaxy's core. Inside them, charged particles spiral through magnetic fields, producing the radio emission that reveals their shape. The scale of these bubbles is difficult to grasp. They rise far above the disk, forming some of the largest structures in the Milky Way. Their presence shows that the galaxy's center has undergone dramatic episodes that shaped vast regions of space. These giant bubbles act as markers of ancient events whose echoes still linger in the quiet radio glow. There are black hole pairs hidden throughout the galaxy. Black holes are often found not alone but in pairs formed when two massive stars evolve together. As each star reaches the end of its life, it collapses into a black hole. The pair then orbits a common center of gravity, slowly drawing closer as they lose energy through gravitational waves. These hidden systems are difficult to detect because black holes emit no light. Astronomers identify them by observing the motion of nearby stars or by detecting high-energy radiation when one black hole pulls material from a companion star. Some pairs remain quiet for long periods, revealing themselves only through subtle gravitational influences. These binary black holes hold valuable clues about stellar evolution, the death of massive stars, and the conditions that lead to gravitational wave events. Their silent motion adds an air of mystery to the Milky Way. They drift unseen through the galaxy, locked in orbits that will eventually end in a powerful nudger releasing energy across space. Some stars form with entire disks of dust that glow like embers. Young stars often emerge surrounded by disks of dust and gas. These disks glow with gentle warmth as starlight heats the small particles within them. The dust absorbs energy and re-radiates it in infrared wavelengths, creating a soft ember-like glow. These disks are the birthplaces of planets. Over time, dust grains collide and stick together, forming larger clumps that grow into planetesimals and eventually full planets. The structure of these disks can reveal the earliest stages of planetary formation. Rings, gaps, and spirals may appear as new worlds carve paths through the dust. Observing these glowing disks helps astronomers understand how solar systems emerge from simple clouds of material. They show that planets begin as tiny grains drifting in warm, swirling environments. These softly lit disks offer a glimpse into the beginning of worlds, shining as delicate halos around the stars they nourish. Dust hides vast regions of star formation. The Milky Way is full of light we cannot see. Interstellar dust, made of microscopic grains of carbon, silicates, and ice, weaves through the galaxy in clouds and tendrils. Invisible light, it obscures vast regions of space, blotting out stars and entire nebulae. But behind this veil, star formation continues. Infrared telescopes can peer through the dust, revealing glittering nurseries filled with newborn suns. What looks like darkness is often a cradle. The dust, though it hides, is part of the process, absorbing energy, helping gas cool, and shielding delicate stages of stellar birth. What seems like emptiness is often the beginning of something bright. There are starless gas clouds drifting through the galaxy. Not every cloud of gas becomes a star. Across the Milky Way, astronomers have found massive, cold clouds that seem destined for collapse, yet remain dark and dormant. Some are too diffuse. Others may be stabilized by magnetic fields or internal turbulence. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen but untouched by fusion. They may one day ignite, or they may drift until torn apart by external forces, their gas recycled into other regions. In these clouds, the galaxy holds its breath, waiting perhaps for the right nudge to spark something new. The Milky Way recycles matter across generations. Stars are not permanent. They live, burn, and die. And in dying, they return their material to the galaxy. Supernova spread heavy elements. Red giants shed outer layers. Planetary nebulae drift outward into space. This enriched material joins the interstellar medium, where it cools, condenses, and eventually forms new stars, planets, and even life. Every atom in your body has passed through this cycle, born in a star, scattered into space, gathered into new form. The Milky Way is not a static stage, but a great engine of renewal. It breathes in time with its stars, making, unmaking, and beginning again. Metal-poor stars hold clues to the early universe. In astronomy, metals are not just iron or gold, they are any elements heavier than helium. The earliest stars in the universe had almost none of these metals, because they formed before earlier generations of stars had a chance to forge and scatter them. Today, astronomers seek out metal-poor stars in the halo of the Milky Way. These stars, faint and ancient, preserve the chemical conditions of a time long gone. By analyzing their composition, we peer into the primordial past, into the period just after the Big Bang, before galaxies had matured, before the galaxy itself had taken full shape. They are fossils made of light. Ancient supernova debris still drifts through the Milky Way. When massive stars explode, they send debris far into the galaxy. This material includes heavy elements that were forged inside the star before it died. Over time, the debris spreads out, forming filaments and clouds that drift through the interstellar medium. Some of this material mixes with molecular clouds, becoming part of the next generation of stars and planets. Other fragments remain isolated, glowing softly as they cool. Studying these remnants helps astronomers understand the composition of supernovas and how elements move through the galaxy. These drifting clouds can be detected in many wavelengths, from radio waves to X-rays, depending on their temperature and structure. They serve as markers of the powerful events that shaped the chemical landscape of the Milky Way. The debris acts as a bridge between generations of stars, carrying the legacy of long-dead giants into the future. Even after millions of years, these remnants continue to influence the evolution of the galaxy. There are stellar bow shocks created when stars plow through gas. As some stars move rapidly through the galaxy, they encounter clouds of gas that stand in their path. The interaction creates a bow-shaped shock wave, similar to the wave formed by a boat moving through water. This shock compresses and heats the gas, causing it to glow in infrared or visible light. The shape and brightness of the bow shock depend on the star's speed, wind strength, and the density of the surrounding material. These structures reveal important information about both the star and its environment. They show how stellar winds push against the interstellar medium and how stars respond to the gas around them. Some bow shocks stretch across light years, forming graceful arcs that mark the star's motion. Observing them helps astronomers track runaway stars and understand how high-speed interactions shape the galaxy. These luminous curves offer a reminder that even the motion of stars can paint patterns in the surrounding gas. The Milky Way contains massive hot stars that live fast and die young. Among the stars in the galaxy are a rare group of giants that burn their fuel at an incredible rate. These massive hot stars shine with intense brightness and produce strong stellar winds that shape their surroundings. Because they consume their hydrogen quickly, they live only a few million years, a brief moment in cosmic terms. Their ultraviolet radiation influences nearby clouds, triggering star formation or halting it depending on the conditions. When these stars reach the end of their lives, they explode as powerful supernovas, releasing heavy elements into the interstellar medium. Studying them helps astronomers understand how energy flows through the galaxy. Their short but intense lives play an important role in the evolution of surrounding regions. They sculpt nebulae, enrich the galaxy, and leave behind compact remnants such as neutron stars or black holes. These fast-living giants show that not all stars follow gentle paths. Some blaze brilliantly for a brief time, leaving lasting marks on the Milky Way. Some worlds experience constant storms larger than Earth. Across the galaxy, there are planets where storms never truly end. These colossal weather systems can span distances larger than Earth itself and may persist for years or even centuries. Many of these worlds are gas giants with thick atmospheres dominated by strong winds and powerful jet streams. The storms form where bands of atmospheric motion collide, creating swirling vortices that grow into immense cyclones. Some storms appear as bright or dark spots that shift in size and shape over time. Their colors reflect the chemical composition of the clouds and the temperatures within the storm. Studying these massive weather systems helps astronomers understand the dynamics of planetary atmospheres under different conditions. The presence of such storms shows how lively and turbulent distant worlds can be. These powerful systems remind us that weather in the Milky Way is not limited to gentle breezes or moderate rains. Instead, some planets host storms with scales and energies far beyond anything experienced on Earth. Rogue stars are flung from the core. Most stars drift calmly through the galaxy, but a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. These are hypervelocity stars. Some are the remnants of binary systems disrupted by the supermassive black hole at the center of the galaxy. One star falls in and vanishes. The other is slingshotted outward, hurled into the dark at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into intergalactic night. Star formation is slowing down. Long ago, the Milky Way was more active, bursting with fresh stars born from dense, collapsing clouds. But in recent epochs, the pace has slowed. There is still gas available, but much of it is spread thin, heated, or locked in forms that resist collapse. The galaxy is not done making stars, but it is settling. Astronomers estimate that star formation peaked billions of years ago and has been declining ever since. This does not mean the end is near, only that we live in a quieter chapter. A mature spiral, glowing gently in its middle age, still forming stars, but no longer in a hurry. Some stars formed before the Milky Way had a disk. The disk, the broad, flat spiral we think of as the Milky Way, formed gradually over time. But some of the stars in our galaxy are older than the disk itself. These ancient stars reside mostly in the halo or the thick disk, and they formed when the galaxy was still assembling, a loose cloud of stars, gas, and dark matter slowly collapsing inward. By studying their composition and motion, astronomers can peer back into the era before structure, before spirals. These stars are the elders of the galaxy, silent witnesses to its birth and the long, slow shaping of what we now call home. A galactic year is about 225 to 250 million Earth years. As the Sun orbits the center of the Milky Way, It completes one full revolution every few 100 million years. This is called a galactic year, a vast cycle of motion that dwarfs all our calendars. In the time it takes for the Sun to circle the galaxy once, continents drift, species rise and fall, and entire epochs unfold. It is thought that we are currently about halfway through one such orbit. The last time the solar system was in this part of its path, the supercontinent Pangaea had just begun to break apart, and dinosaurs had not yet emerged. A galactic year is the slow heartbeat of cosmic time. There are regions where stars form in chains like beads. In some areas of the Milky Way, stars do not form in clusters or scattered groups, but instead appear in long, narrow chains. These bead-like formations arise when gas in a molecular cloud becomes compressed along a single filament. As the filament contracts, it breaks into regularly spaced pockets that collapse into stars. The result is a line of newborn stars following the shape of the original gas structure. Observing these chains reveals how gravity, turbulence, and magnetic fields work together during star formation. The evenly spaced stars provide clues about the conditions inside the filament before it broke apart. These formations change over time as the young stars ignite, and their radiation shapes the surrounding gas. Chains of newborn stars help astronomers understand how large-scale structures within the galaxy influence small-scale events. They show that even simple lines of gas can give rise to elegant and orderly patterns of starlight. These beaded stellar regions add a delicate beauty to the Milky Way's star-forming areas. The galaxy contains enormous clouds that block entire patches of starlight. The Milky Way holds giant clouds of dust and gas so thick that they obscure all the stars behind them. These dark nebulae appear as empty spaces when viewed from Earth, yet they are full of material. The dust grains inside absorb and scatter visible light, hiding entire regions of the galaxy from sight. Inside these clouds, temperatures are extremely low, allowing molecules to form in sheltered environments. Over time, gravity can cause parts of the cloud to collapse and create new stars. Although these regions look empty, they are among the most active and important parts of the galaxy. Infrared and radio observations reveal the hidden structures inside them, showing dense knots of gas where future stars will ignite. These massive clouds shape the appearance of the Milky Way, carving dark lanes through the bright band of starlight. Their quiet presence reminds us that what looks like darkness can often hold the beginnings of creation. Some red dwarfs burn so slowly they could outlive the universe we know. Red dwarfs are the smallest and coolest stars capable of sustaining nuclear fusion. Their low mass makes them incredibly efficient at using their hydrogen fuel. As a result, they burn at a slow, steady pace and can live for trillions of years. This lifespan far exceeds the current age of the universe. Many red dwarfs that form today will still shine long after more massive stars have faded into remnants. Their gentle glow and stable radiation make them common hosts for planets. Because they live so long, any worlds orbiting them have enormous spans of time to evolve. Studying red dwarfs helps astronomers understand stellar lifetimes and the future of the galaxy. These stars are quiet, persistent sources of light that dominate the Milky Way's population. Their endurance provides a sense of cosmic continuity and hints at how the galaxy might look in distant epochs when only long-lived stars remain. The Milky Way holds hidden star factories buried in dark dust. Deep within the densest clouds of dust, the galaxy hides star-forming regions invisible to ordinary telescopes. These hidden star factories are so well shrouded that even starlight from newborn suns cannot escape invisible wavelengths. Infrared observations reveal their presence, uncovering clusters of young stars still in the early phases of formation. Inside these dark regions, gas collapses under gravity, assembling new stars from cold material. The surrounding dust plays an important role by shielding the forming stars from harsh radiation. As the stars grow, their winds gradually carve openings through the dust, allowing their light to emerge. These concealed nurseries are among the most active areas in the galaxy, producing new generations of stars that will eventually populate the spiral arms. They remind us that much of the Milky Way's activity occurs behind thick veils of dust, far from direct view. Stars orbit the galaxy at different speeds. Unlike planets in a solar system, which follow neat tracks around their star, stars in the Milky Way move with more freedom. Some race ahead in the inner regions. Others drift slowly along the outskirts. This difference in speed is why spiral arms form. They're not solid structures, but patterns, like slow traffic jams of stars and gas moving through space. As these density waves pass, they trigger new stars to form, lighting up the arms in curls of blue and white. Our own sun is part of this swirl, moving in and out of these patterns across time. The galaxy is not a clock. It is a current, and we are drifting in it. The galaxy holds together because of something we cannot see. By all logic, the Milky Way should not exist. Based on what we can measure, stars, dust, gas, the outer edges of the galaxy are spinning too fast. They should be flung into space, scattered like leaves in a storm. And yet they remain. The answer is dark matter. This mysterious substance does not shine, reflect, or emit any light. But it exerts gravity. And there is so much of it that it outweighs all the visible matter in the galaxy many times over. We don't know what dark matter is, but we know that without it, the Milky Way would fly apart. It is the invisible scaffolding that holds everything in place. There's a supermassive black hole at the core. At the very center of the Milky Way lies an enormous black hole, a singular point of gravity called Sagittarius A*. It is more than 4 million times the mass of the Sun, yet it occupies a space smaller than the orbit of Mercury. We cannot see it directly, but we've watched nearby stars whip around it at tremendous speeds, tracing invisible loops through the void. Sometimes gas and dust fall inward and flare with X-rays as they spiral into the event horizon. For now, Sagittarius A* sleeps, but long ago, it may have burned like a quasar, lighting up the galaxy from within. It is the silent conductor of the Milky Way's heart, pulling stars into slow, relentless dance. The Milky Way has a peanut-shaped bulge. When astronomers mapped the center of the galaxy, they discovered something unexpected. The central bulge is not a smooth, round ball of stars, but a three-dimensional peanut shape. Seen from the side, it swells in the middle and narrows at the ends, like a twisting hourglass made of stars. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly, buckling and puffing upward over time. These inner structures are sculpted by gravity, billions of years of motion, and the accumulated rhythm of stellar orbits. We live in a spiral galaxy, but its heart is full of complexity, not flat or clean, but intricate and alive. There are stars here that form in triple systems. In some regions of the Milky Way, stars do not form in pairs or alone, but in groups of 3 bound together by gravity. These triple systems begin inside dense clouds where several fragments collapse at nearly the same time. Depending on their masses and distances, the 3 stars can arrange themselves in stable patterns. Often 2 stars orbit closely while the third travels farther out. In other cases, all 3 follow elongated paths that weave around their shared center of gravity. These intricate motions can remain stable for millions or even billions of years. Studying triple systems helps astronomers understand how stars influence one another from their earliest stages. Their interactions can affect the formation of planets, shaping their orbits or preventing them from forming entirely. Some triple systems become unstable as the stars evolve, eventually breaking apart and sending one member drifting into the galaxy. Others remain connected for their entire lifetimes. These groups reveal the complex and varied environments in which stars are born. They show that gravity often creates arrangements far more intricate than simple solitary stars. Some worlds orbit their stars on paths so eccentric they freeze and boil in 1 year. There are planets in the Milky Way that follow extremely stretched orbits. Instead of circling their stars in nearly circular paths, they move along ellipses that carry them from distant cold regions to scorching close approaches during each orbit. When these planets travel far from their stars, their atmospheres can freeze, forming layers of frost or thick clouds of ice crystals. As they swing inward again, temperatures rise rapidly. Ice melts, gases expand, and entire atmospheres can shift in a matter of weeks. These dramatic fluctuations create environments unlike anything on Earth. The surfaces or skies of such worlds constantly transform, shaped by cycles of boiling heat and freezing cold. Eccentric orbits often form through close encounters with other planets or the gravitational pull of distant companions. Studying these wild paths helps astronomers understand how planetary systems evolve after chaotic interactions. These extreme worlds reveal how profoundly orbital shape can influence climate and habitability. The galaxy contains clouds heated by invisible radiation from distant events. Across the Milky Way, there are clouds of gas warmed by radiation from sources so far away that the heating effect seems almost mysterious. These clouds do not always lie near young stars or supernovas, yet they glow with temperatures higher than expected. Their warmth comes from high-energy photons traveling long distances through space. These photons can originate from ancient explosions, active regions near the galactic center, or compact objects that emit powerful radiation. When the photons encounter gas, they transfer energy and cause the cloud to heat. Observing these warmed regions helps astronomers map the flow of radiation across the galaxy. It reveals how past events continue to influence areas far removed from their sources. These heated clouds act as delicate traces of energy that moves silently through space. They show that the Milky Way is filled with subtle interactions between light and matter, even in regions that appear quiet and dark. Some planets are sculpted by tidal forces into distorted shapes. When a planet orbits very close to its star or shares its system with a massive companion, tidal forces can stretch it out of a perfect sphere. These forces arise from the uneven pull of gravity across the planet's surface. The side facing the star feels a stronger tug, while the far side feels less. Over time, the planet can become elongated, taking on a shape slightly like an egg or tear. This distortion affects the planet's interior, generating heat through friction. The extra warmth can drive volcanic activity or alter atmospheric circulation. Some distorted planets orbit so close to their stars that one side remains permanently heated, while the stretched shape enhances the temperature difference. Observing these worlds helps astronomers understand how gravity shapes planetary bodies. They show that planets are not always round, and that intense gravitational interactions can sculpt entire worlds into unusual forms. Rogue stars are flung from the core. Most stars drift calmly through the galaxy, but a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. These are hypervelocity stars. Some are the remnants of binary systems disrupted by the supermassive black hole at the center of the galaxy. One star falls in and vanishes. The other is slingshotted outward, hurled into the dark at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into intergalactic night. The Milky Way and Andromeda are on a collision course. High above the horizon, the Andromeda galaxy appears as a faint blur to the naked eye, a spiral much like our own, lying over 2 million light-years away. And yet, it is moving steadily toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide. It won't be violent in the way you might imagine. Stars are spaced too far apart to crash directly. But their gravity will warp both galaxies into long, stretching arcs. Tidal tails will curl outward. Black holes may spiral together. And after billions of years, the two galaxies will merge into a single, larger system. It will be a slow, elegant dance, the future of our home written across the stars. Some stars orbit backward. Most stars in the Milky Way orbit the center in the same general direction. But not all follow the rules. Some stars, especially in the outer halo, move in retrograde, orbiting opposite to the galaxy's main rotation. These stars likely arrived from elsewhere, born in dwarf galaxies that were later absorbed. Their reversed motion is a quiet signature of their foreign origin. It's as if the galaxy carries old memories in its motion, stories of ancient mergers and cosmic encounters, preserved not in light, but in the slow, patient turning of stars against the stream. The Milky Way may have eaten dozens of dwarf galaxies. Over billions of years, the Milky Way has not grown alone. It has consumed. Small galaxies, faint, low-mass companions, have drifted close, been caught in its gravity, and slowly dismantled. Their stars are now part of our halo, disk, or stellar streams. Astronomers have identified several of these mergers by analyzing stellar motion and composition. One especially large event, the Gia-Enceladus merger, added many stars and may have reshaped the early structure of the galaxy. The Milky Way is not a pristine spiral. It is a composite, built from quiet collisions, stitched together from the remains of many smaller worlds. There are star-forming filaments that stretch like cosmic threads. In the Milky Way, some of the most active star-forming regions take the shape of long, narrow filaments. These structures can stretch for many light-years, filled with cold gas on the brink of collapse. Gravity slowly pulls parts of the filament inward, creating nodes where stars begin to form. The filament itself acts like a spine, feeding material to these growing cores. Observing these cosmic threads helps astronomers understand how large-scale structures in molecular clouds guide the birth of stars. They reveal that star formation is often organized, following the flow of gas along elongated pathways. These filaments create a sense of order in the apparent chaos of interstellar clouds, shaping the locations where new generations of stars ignite. Some stars live entire lives in near-perfect isolation. While many stars form in clusters or associations, some drift so far from other stars that they spend their whole lifetimes almost alone. These isolated stars rarely interact with passing objects. Their environments remain calm, free from nearby radiation or gravitational disturbances. Studying them provides insight into how stars evolve without outside influence. Their planets, if they have any, may experience unusually stable conditions. These quiet stars move slowly through the galaxy, following gentle orbits that keep them far from crowded regions. Their isolation reveals the wide range of environments that exist in the Milky Way. They remind us that not all stars share their space with neighbors. Some shine alone from birth to death, carrying their solitary light across billions of years. The Milky Way holds ancient stellar fossils preserved in their original chemistry. Scattered throughout the Milky Way are stars so old that they preserve the chemical conditions of the early universe. These stellar fossils formed before the galaxy had enriched itself with heavy elements. Their atmospheres contain almost nothing beyond hydrogen and helium, along with traces of a few other elements created shortly after the universe began. Because they have remained unchanged for billions of years, these stars offer a direct window into the past. Their faint light carries information about the primordial environment from which the first stars arose. Many live in the galactic halo where the density of gas and radiation is low enough that they have avoided disturbance. Their stable structures and simple chemistry allow astronomers to measure the earliest patterns of star formation. These ancient stars show how the Milky Way grew from small beginnings into the spiral galaxy we know today. They remind us that even now, ancient relics of cosmic history drift quietly through the galaxy, glowing with the untouched chemistry of the first generations of starlight. Some worlds orbit stars that are barely stable. In certain systems within the Milky Way, planets revolve around stars that live on the edge of instability. These stars may be rapidly burning through their fuel, expanding into early giant phases, or oscillating between different states of brightness. Their internal layers shift and pulse, creating turbulent conditions that can influence orbiting planets. Some of these stars release sudden bursts of energy that alter the temperature and chemistry of the surrounding space. Others experience gradual swelling or contraction that changes their luminosity over long periods. Planets orbiting such stars face environments far more variable than Earth's. Their climates may shift dramatically as the star's output changes. Studying these systems helps astronomers understand how planets adapt to unpredictable sources of radiation. It also reveals the delicate balance required for a star to remain stable. These barely steady suns add complexity to the Milky Way's population, showing that not all stars offer quiet and predictable light. Some shine with restless energy that shapes the worlds around them in surprising ways. There are regions where gravity shapes clouds into sculpted pillars. In many star-forming regions of the Milky Way, vast clouds of gas and dust take on towering, sculpted shapes. These pillars form when intense radiation and winds from nearby massive stars carve away the surrounding material. The denser parts of the cloud resist erosion and remain standing as elongated columns. Gravity within these pillars pulls material inward, causing new stars to form at their tips or deep inside their sheltered cores. Over time, the pillars may stretch, twist, or fragment as radiation continues to shape them. Observing these structures helps astronomers understand how powerful forces guide star formation. Their dramatic shapes reveal where young stars are influencing their environment and where new generations are about to emerge. These sculpted forms highlight the delicate balance between creation and erosion in the galaxy. They stand as intricate carvings of gas and dust, shaped by light, gravity, and the turbulent flow of stellar energy. The galaxy contains stars with exotic element atmospheres. Certain stars in the Milky Way display chemical compositions, unlike those seen in typical stellar atmospheres. Instead of the usual mix dominated by hydrogen and helium, these stars can show strong signatures of rare elements such as carbon, zirconium, strontium, or even heavier atoms forged in unusual nuclear processes. Some of these exotic stars formed from material enriched by ancient collisions of compact objects. Others developed unusual atmospheres through internal mixing or mass transfer from a companion. Their unusual spectra reveal details about the extremes of stellar evolution and the rare conditions that create such elements. Studying these stars helps astronomers trace the pathways through which heavy elements spread across the galaxy. Their distinctive chemical fingerprints act as clues to events that occurred long before the Sun existed. These stars demonstrate the incredible diversity of stellar compositions found in the Milky Way. Their exotic atmospheres glow with the products of rare cosmic processes, offering a glimpse into the most unusual forms of starlight. Some planetary rings stretch wider than Earth's orbit. In the Milky Way, there are worlds whose ring systems dwarf anything seen in our solar system. These rings can extend distances larger than the orbit of Earth around the Sun. They consist of dust, ice, and rocky fragments spread across vast regions of space. Such massive rings commonly form around young planets still gathering material, or around worlds that have captured debris from nearby objects. Their structure is shaped by the planet's gravity, the motion of small moons, and the influence of stellar radiation. Observing these rings reveals the processes that sculpt planetary systems during their early stages. The size of the rings suggests that many worlds undergo dramatic periods of collision and fragmentation. These enormous structures shimmer faintly in starlight, forming broad, delicate halos that sweep across their host planets. They demonstrate the incredible range of scale that exists among planetary systems, far surpassing the familiar rings of Saturn. The Milky Way holds stellar remnants that drift slowly through the dark. After stars exhaust their fuel, some collapse into compact remnants that emit only faint light. These stellar remains include white dwarfs, neutron stars, and black holes that move quietly through the galaxy. Many drift alone, far from where they were born. Their slow journeys carry them through regions of different density and temperature. Some pass through clouds of gas, gathering thin layers of material that produce soft emissions. Others remain nearly invisible, detectable only through gravitational effects on nearby objects. Studying these remnants reveals the long-term evolution of stars and the fate of stellar material. Their presence reminds us that the galaxy contains not only bright and youthful stars, but also ancient survivors of past stellar generations. These drifting remnants embody the final stages of stellar life, moving gently through the darkness long after their parent stars have faded. Some solar systems form with multiple giant planets crowded together. In certain areas of the Milky Way, young stars give rise to systems filled with several giant planets packed into tight orbits. These worlds may begin as large clumps of gas and dust scattered across a disk, growing rapidly as they gather material. When many giants form at once, their gravitational interactions create a dynamic environment. They can push each other into new orbits, swap positions, or even eject one another into deep space. Some systems eventually settle into stable configurations. Others remain chaotic for millions of years. Studying these closely packed systems helps astronomers understand how planetary architectures emerge from complex beginnings. The presence of multiple giants in tight arrangements reveals how flexible and varied planetary formation can be. These crowded systems show that not all solar systems grow with orderly spacing. Some begin as bustling neighborhoods shaped by constant motion and gravitational negotiation. The galaxy contains high-energy arcs formed by magnetic whiplash. In some regions of the Milky Way, magnetic fields twist and snap under intense pressure. When this happens, the sudden release of energy creates arcs of glowing gas that sweep across space. These arcs form when magnetic lines become tangled and then rapidly realign. The process accelerates charged particles, causing them to emit light in radio or X-ray wavelengths. These high-energy arcs may appear near young stars, supernova remnants, or dense regions where magnetic fields are especially strong. Observing them helps astronomers understand how magnetic energy shapes the interstellar medium. The arcs reveal the hidden forces that influence gas clouds, radiation, and cosmic rays. Their appearance adds a sense of dynamism to the Milky Way, showing that even invisible magnetic structures can produce dramatic and beautiful effects. Some stars shed jets that stretch across space for many light years. Certain stars generate narrow jets of material that extend deep into the surrounding space. These jets form when gas spirals onto the star through a rotating disk. Magnetic fields then focus part of the material into thin, fast-moving streams that shoot away at high speeds. In some cases, these jets grow to lengths of many light-years, carving tunnels through nearby clouds. The jets can glow brightly where they collide with gas, forming knots and arcs of light that drift over time. Observing these structures helps astronomers understand how stars grow and how energy moves through star-forming regions. The jets reveal the influence of magnetism and rotation during the early stages of stellar development. Their immense reach demonstrates the power that even young stars can exert on their surroundings. The Milky Way holds worlds that form in darkness, far from any starlight. Not all planets form close to bright stars. Some take shape in the outer reaches of young systems where sunlight is weak or nearly absent. In these distant regions, gas and dust can gather into planets that never receive strong radiation. Their surfaces remain cold, and their atmospheres develop under dim illumination. Some of these worlds may eventually drift inward toward warmer zones. Others remain in permanent darkness, orbiting far from any comforting heat. The conditions under which they form differ greatly from the environments near stars. Studying these distant planets helps astronomers understand the full range of planetary birthplaces. These shadowed worlds show that planet formation is not limited to bright and active regions. Even the cold outer edges of disks can create fully formed worlds that move in deep quiet, far from the warmth of starlight. As we come to the end of our journey tonight, you don't need to hold on to any of it too tightly. The facts can loosen their grip now, the way a hand relaxes after carrying something for a while. What matters is the feeling they leave behind, that quiet sense of scale, that soft widening of the mind. We spent this time drifting through the Milky Way, our vast river of starlight, not as a distant picture, but as a home you are already inside. We wandered through ideas of ancient stars that have been traveling longer than Earth has existed, and through the slow, steady motion that carries our solar system along its path. We lingered on the way the galaxy continues to change, gathering, reshaping, and growing, even now, in ways too gradual to notice from one lifetime. We touched the mystery of its spiral structure, the parts that are hard to see from within, blurred by dust and distance, like trying to understand a forest while standing between the trees. And in the spaces between those thoughts, there was imagery too. Dust clouds faintly lit like fog caught in moonlight. Halo stars moving high above the galactic plane, quiet and patient. Hidden worlds roaming without a sun, drifting in darkness with only their own slow warmth. The distant center, crowded and powerful, wrapped in dust, where strange forces gather and time feels different. All of it stitched together by gravity, like a deep fabric holding every moving piece in place. Now it's time to let those pictures soften. Let them fade gently, like the Milky Way itself fading at the edge of your vision when your eyes begin to close. If your mind is still awake, it can simply float with one last simple image: a calm night sky, a pale band of light arcing overhead. Not loud, not demanding, just present. The kind of presence that makes your problems feel smaller without dismissing them. The kind of scale that makes you feel held, not lost. If your thoughts keep returning to details, that's okay. You can let them pass, like stars sliding by a window on a long, quiet train ride. Nothing needs solving tonight. Nothing needs finishing. The galaxy will keep turning whether you follow every idea or let them drift away. Stars will continue their patient orbits. Dust will continue its slow dance. Light will keep traveling, taking its time, never hurrying, never forcing its way forward. So take that same permission for yourself. Let your breathing become the only thing you pay attention to for a moment. Not controlling it, just noticing it. In and out. Slow, steady, easy. With each exhale, allow your shoulders to drop a little more. Allow the muscles in your face to smooth out. Let your jaw unclench. Let your hands rest heavier. Let your legs sink into stillness. If the day left any sharp edges in you, let them round off now, softened by the quiet. Imagine yourself somewhere far from streetlights, where the sky is truly dark. The Milky Way is there like a faint, snowy ribbon, stretched across the night. You don't need to understand it. You don't need to measure it. You can simply let it exist above you, vast and calm, while you do the simplest human thing of all. You rest. If you enjoyed this gentle journey, a quiet way to support the channel is to tap like, subscribe, or leave a soft comment before you drift off. It helps other sleepy minds find their way here too, one soul at a time, looking for something calm to hold on to at the end of the day. And if you happen to still be awake, there will be another video waiting for you on the screen. You can let that be the next step in the journey, another slow drift through the wonders of space, carried by the same gentle pace, the same quiet curiosity. If sleep is already close, you don't need to reach for anything. Let it come the way night always comes. Gradually, kindly, without effort. The Milky Way will still be there tomorrow night, and the night after that, turning softly, holding its secrets, carrying you along, whether you notice or not. Sleep well, and good night.